Hi everyone, this video is a compilation of all of my Chapter 3 lectures from Chapter 3 in College Algebra and Trigonometry, the 4th edition by J.S. Ratty, Marcus McWaters, and Les Skurzepek. So again, this video is very long because it's a compilation of 6 lectures. If you're looking for each individual lecture, I'm going to post a link in the description to the individual videos in a playlist, so don't be discouraged because this video is so long. It's because it's a compilation. I have it up in case you want to digest it in long form, but again, if you're looking for the individual ones, the individual videos, they will be in the description. So thanks so much for watching, and let's get
Hi everyone, welcome to the beginning of Chapter 3 with Section 3.1. This is going to be the last chapter for this college algebra class that I'm doing these lectures for. If we were to ever do pre-calculus, we would do Chapter 4 in this book, but alas, we will stop here for now. So Chapter 3, 6 sections. 2 of those sections we're going to combine into one lecture. It just makes a little bit more sense. It it eliminates a little bit of the weird sequencing. So we'll get to there when we get there. But for now, sections 1, 2, and 3 in Chapter 3 are all on their own. So what we're going to do is start with quadratic functions, and then we're going to move to polynomial functions. So quadratic functions, degree 2, and then we'll work our way up to polynomials, which could be any degree. Do something a little different in 3.3, but then we start to wrap up the entire course when it comes to 3.4. So let's do quadratic functions. In Chapter P, we had ax squared plus bx plus c, the expression. In Chapter 1, we had ax squared plus bx plus c equals 0, the equation. In Chapter 2, we had f of x equals ax squared plus bx plus c, specifically the function. But what we have here in Chapter 3 is also a function, right? The name of the section is quadratic functions, but it's going to look a little different now. Okay, so this is what we call general form for quadratic functions, and we get this via completing the square. So we'll do a couple examples of this. We haven't talked about completing the square since I think 1.3. It's been a really long time, but we'll get there when we get there. But this is going to be what we focus on here in Chapter 3.1, but also we'll see a couple times where we can use the original form. So standard form is that original form we used to work with, ax squared plus bx plus c, but here in 3.1 we want to focus on general form, a times x minus h squared plus k. H is the horizontal shift, a is the stretch or compression and x-axis reflection, and k is the vertical shift. So all of these things would have been relevant when we did 2.7, when we did transformations, but we actually have specific meanings for some of these things now. Specifically, h comma k is going to be our vertex of the parabola. So we have a general idea as to what quadratics look like, right? They look like parabolas. They open up or they might open down, but the place where it changes from decreasing to increasing or increasing to decreasing is called the vertex. Now, the place where that vertex occurs in the function would be h comma k. Now, just want to stress, this is minus h. If you have x minus h, h would then be positive. It's backwards, but for plus k, it is intuitive. So, right, go back to that, like the 2.7 stuff where we said intuitive for horizontal, not intuitive. Sorry, intuitive for vertical, not intuitive for horizontal. Okay, h, if we don't have it in this form, h in this form occurs at negative b over 2a. So let's say you're given standard form and you don't know what the vertex is. Here, the vertex is as simple as just reading it. But in standard form, the vertex would occur at negative b over 2 times a. Now, k, well, k would just be the value at h. So you can find the x-coordinate of the vertex, right, the h-coordinate, by doing negative b over 2a, and then you find its respective y value by just plugging in that h value into your function, right? X, y, that makes a lot of sense. X equals h we refer to as the axis of symmetry. I personally don't spend a whole lot of time with this, but it's actually a way that you could shortcut graphing quadratic functions. And I'll talk about it when we go to graph them, but in most cases, it's a little bit easier to talk about everything else. K is either the minimum or maximum value based on the value of a. So we saw in 2.7 that if a were to be positive, our graph would be a regular parabola, in that case, the value right at the bottom, the vertex would be a minimum, right? Here's your parabola. Well, we have a minimum value right here. And likewise, if a is negative, it reflects over the x-axis. And in that case, k would be the maximum value. So let's do some examples of converting to general form and converting to standard form. So general form is that a times x minus h squared plus k notation. So here's what we're going to do. We need to complete the square. We said in 1.3, completing the square, you don't ever have to do. It's one of those things that you could do if you wanted to use the square root property to solve equations, but odds are, if you're in that situation, you're probably just going to go for quadratic formula anyway, since it works way more frequently and works way more consistently. So completing the square says this. If for ax squared plus bx plus c, we are going to add and subtract b over 2 squared, because what that's going to do is help us get a perfect square term. So don't believe me right now, that's okay. So in this case, ax squared plus bx plus c, b is 6. So what we're going to add and subtract is b divided by 2, the whole thing squared. In this case, b is 6. So we are going to add and subtract 6 divided by 2 squared. And again, we have to add and subtract it. Well, if we add this thing and subtract this thing, well, they would just cancel out. So it's like we added 0. And we know that if we add 0 to anything, it doesn't change the value. Okay, well, we know that 6 divided by 2 is 3. 3 squared is 9. And now let's group these three terms together, because you might notice something about these three terms. You might notice that if we wanted to factor this, this is a nice perfect square factor. Okay, x squared plus 6x plus 9 is x plus 3 squared. And then everything on the outside, minus 9 plus 7, is minus 2. Okay, so we went from standard form to general form. And what we can do now is we can pull the vertex from this a lot quicker. You could do h equals negative b over 2a and then plug that value in, but that can be a lot of work. So now, since we've already converted, let's take the vertex from here. The vertex is always x minus h and then plus k on the outside. Well, normally it's x minus h, but here we have x plus 3. That means the x value of the vertex will be negative 3, backwards for the x value. Kind of, again, think about the intuition part of 2.7. However, the y coordinate is, as you would expect, it is intuitive. So we would get negative 3 for x and negative 2 for y. Again, sign is backwards for x, sign is as it makes sense for y. X minus h is minus 3, since this is plus 3, and k is negative 2. Okay, so let's do another example of converting to general form. The one rule that we had when it came to completing the square is that if we were to complete the square, a needs to be 1. Well, a here is 5. So that means we don't have to complete the square, right? It's all over, we're done? No. What we can do is just take out 5 from the first two terms, right? Think about when we were completing the square in the last example, the only thing we were interested in was that middle term b. We don't even need to touch that plus 8. Okay, well, let's complete the square on the inside. B, the coefficient attached to x, is negative 4. So what we're going to add and subtract is negative 4 divided by 2 squared. We're going to add and subtract it on the inside of these parentheses. Okay, negative 4 divided by 2 is negative 2. Negative 2 squared is positive 4. So we're adding and subtracting 4. But what we're now going to do is we see this is our perfect square, but we have this extra minus 4 out here. We don't want that extra minus 4. What we can do is pull out this minus 4, but notice that this minus 4 is stuck inside this 5. So if we're pulling out negative 4, what we're really pulling out is 5 times negative 4. So be very careful about that. Okay, well, this is a perfect square. Here, 5 times 4 is negative 20. Perfect square, and combine everything on the outside. We get x minus 2 squared and negative 12. Pretty nice. And now we can get the vertex from this. Again, x minus h means that h is positive. So since we have x minus 2, h is positive 2. And k, well, k is negative 12. So we get 2 comma negative 12. Again, keep in mind the quirks of, the vertex stuff when it comes to hk. Okay. Let's do an example where we write a quadratic function in general form if we were given some information. So we're given the vertex here, and we want to find the version of this quadratic function that has this vertex that passes through this point specifically. Well, what's really nice is this is kind of like writing linear equations. We're given 2 points, and we just plug some information in. However, we're going to have to treat this a little different. Well, let's start with the vertex. Vertex is hk, so h is negative 3, k is 4. And the point that we're given is negative 4, 7. So x is negative 4, and f of x, or y, right? F of x and y are interchangeable. F of x is 7. Well, general form for a quadratic equation is as follows. And notice, well, we have f of x, we have x, we have h, and we have k. The only thing that we're missing is this a. So think back to when we were writing equations of lines and we said, okay, we found the slope, we have a point, we need to plug everything in to find b. Okay, same kind of idea, except we're not looking for b anymore. Now we're going to look for a. So let's plug in all of this information that we know. F of x is 7. A, we don't know. We're going to solve for a. X is negative 4. H is negative 3. And k is positive 4. Okay, and now we just solve for a. Negative 4 minus negative 3 is negative 4 plus 3. Negative 4 plus 3 is negative 1. Well, negative 1 squared is positive 1, so a times 1 is just a. And then we subtract 4 on both sides to get a equals 3. All right, well, in general, this is what quadratic functions are. And when we were going to write the equation of a quadratic function, we need a, we need h, and we need k. All right, well, we just found a, h is negative 3, and k is 4. Last but not least, x minus negative 3, x plus 3. And now you see, here's where the vertex is, and that's where our stretch or compression factor is. So given some information, we can also write equations of quadratics. One more example, this was finding it in general form. If we want to find it in standard form, all we need to do is expand, right? Going from standard to general form is this weird completing the square nonsense. Well, not nonsense, but kind of a pain in the butt, right? But when we are converting to standard form, when we just want to get ax squared plus bx plus c, this is just expanding. Well, x plus 3 squared is x plus 3 times x plus 3. This is a chapter P question for us to expand this. That is x squared plus 6x plus 9. We distribute 3, and then 27 plus 4 is 31. So if you want it in general form, there it is. If you want it in standard form, I think standard form is a little bit prettier, even though it's a little less useful in some cases. That is standard form. Let's do another one of these examples. This time, vertex 1, negative 5, and the point is 3, negative 21. Well, in this case, h is 1, k is negative 5. The point x is 3, f of x or y is negative 21. So again, let's plug in all of this information into the general form for quadratic functions. Okay, well, 3 minus 1 is 2. 2 squared is 4. What we can now do is add 5 to both sides and divide both sides by 4 to get a is negative 4. All right, a times x minus h squared. Well, we had the vertex on the previous slide. We have a right here, so we get negative 4 x minus 1 squared minus 5. Not so shabby. If we want to convert this to standard form again, this is just expansion. So let's expand x minus 1 times x minus 1. Let's distribute negative 4, And last but not least, negative 4 minus 5 is negative 9. Not super scary. So those are some basics to quadratic functions, but what we're going to be interested in doing is graphing. All right, so for us to graph, kind of staying consistent with how we've done things in the past, let's find the vertex, y-intercept, and x-intercepts, and then graph it that way. However, there are some shorter ways that you can graph quadratic functions. I'll point them out, but I'm not going to do any of them here. So just note that there is a shorter way, but I like going this way because it covers all the information that you might be interested in a quadratic function: the vertex, y-intercept, and x-intercepts. Okay, so we have f of x equals negative 3, x plus 2 squared plus 12. Let's start with the vertex. Well, the vertex here, x minus h, so h is negative 2, and k is positive 12. Okay, point 1 down. Y-intercept, well, to find the y-intercept, don't forget that we set x equal to 0. All right, well, f of 0 says wherever we see x, write 0. 0 plus 2 squared, 2 squared, 2 squared is 4. Negative 3 times 4 is negative 12. Negative 12 plus 12 is 0. So when x is 0, y is 0. So our y-intercept is 0, 0. Well, x-intercepts, almost identical, except we're setting y to 0 or f of x equal to 0. All right, a little bit more involved. Let's subtract 12 on both sides. Let's divide both sides by negative 3. Let's take the square root of both sides, but don't forget we get plus and minus. Okay, so we get plus and minus 2. All right, when this is positive 2, 2 equals x plus 2, x equals 0. When this is negative 2, negative 2 equals x plus 2 is negative 4, right? Solving equations. Don't want to spend a whole lot of time talking about that today, but here we go. So we have two x-intercepts, negative 4, 0, and 0, 0. So we have a vertex, we have a y-intercept that happens to also be an x-intercept, and we have another x-intercept. So in general, we're going to talk a little bit more about this in the next section with polynomials, but in general, if you want to graph any polynomial function, you need n plus 1 points. Now, what is n? N is the degree of your polynomial. Again, we got to talk about that a little bit more in the next section. But what I'm getting at here is that if you are graphing a quadratic function of degree 2, you need at least 2 plus 1 points, which is 3. So if you want to graph any quadratic, you need a minimum of 3 points to be able to graph it. Now, you might need more than 3. Your vertex has to be one of those 3 points. But point is, if you know 3 points, most likely you're able to graph, especially if one of those is the vertex. But if you wanted to graph something that is cubic, you would need 4 points. Something to the 4th power, you need 5 points, and so on. Okay, so let's graph all 3 of those points. And here we go. So, and now we know this is a parabola. So there you go. That's how you would graph this quadratic. Now, I mentioned that there is a shorter way to graph, and here it is. Well, I just told you that we need 3 points to graph quadratics. One of them has to be the vertex. Okay, so think about to this last example. We found the vertex, and then we found the y-intercept. So just for a moment, ignore that we found negative 4, 0. If we have negative 2, 12, and 0, 0, what we also know is that the line, the vertical line on which the vertex lies, is the line of symmetry, axis of symmetry for quadratics. What that means is that if you know 1 point to the left or to the right of your vertex, you can reflect it over that axis to get a 3rd point. So what we could have also done is start with negative 2, 12, and 0, 0, and said, okay, 0, 0 is 2 points horizontally from the axis of symmetry. So that means it has an equivalent point 2 units to the other direction of your axis of symmetry. So 0, 0 takes 2 units to get to negative 2, 12. If you go another 2 units, it'll have a reflected point. So with that said, you technically could have graphed knowing 2 points, but you could have found a third point just using symmetry. Now, of course, this is only helpful if you know the vertex. If you don't know the vertex, you have no idea where this graph changes from increasing to decreasing, or in other cases, decreasing to increasing, but that is another option available to you. In my opinion, I personally think that it's very important to know how to find x and y intercepts for your functions. So that's why I prefer to graph this way. But again, that is a quicker way you are able to graph quadratics. Okay, well, let's do another example with 2 times x minus 1 squared minus 4. Let's start with the vertex. Vertex x minus h, okay, h is positive 1, plus k, k is negative 4. Okay, vertex, the easy part. Y-intercept says set x equal to 0. All right, well, wherever we see x, just write 0. 0 minus 1 is negative 1. Negative 1 squared is 1. 2 times 1 is 2. 2 minus 4 is negative 2. So when x is 0, y is negative 2. Okay, so we have 2 points. And again, you know the vertex, you know the y-intercept. You can technically graph from here. But again, I think it's very important to also be able to find x-intercepts. X-intercepts say to set y or f of x equal to 0. All right, let's add 4 to both sides. Let's divide both sides by 2. Let's take the square root of both sides and just add 1 to both sides. So you would need quadratic formula technically to find these x-intercepts. So we have 2 x-intercepts that way. All right, graphing all 4 points that we know now, we can connect them just like that. So notice that we could have done this with just the 2 points. We could have done this with just these bottom 2 points, reflected 0, negative 2, over to 2, negative 2, and graph that way. But also always good use to find our x-intercepts. Okay, well, the last 2 examples we did were in general form. And now we're given one in standard form. Well, we need to convert to general form to be able to answer the same question, right? So let's start by converting to general form. Well, for us to complete the square, we need this a to be 2. So let's factor out 2 just from the first 2 terms. Here, let's complete the square. We're going to add and subtract 4 over 2 squared, right? B divided by 2 squared. 4 over 2 is 2. 2 squared is 4. Okay, we want to pull out this negative 4 because here we have the perfect square. Let's pull out this negative 4, but since this negative 4 is stuck inside this 2, we have to pull out 2 times negative 4. All right, 2 times 4 is 8. And now this is x plus 2 squared, and this is negative 18. Okay, and now we can answer all of the exact same questions. The vertex, x minus h, so h is negative 2, plus k, k is negative 18. Y-intercept, set x equal to 0. So f of 0, 0 plus 2 is 2. 2 squared is 4. 2 times 4 is 8. 8 minus 18 is negative 10. So our y-intercept is at 0, comma, negative 10. X-intercepts, we're going to set f of x equal to 0. All right, let's add 18. Let's divide by 2. Let's take the square root of both sides. And now when this is positive 3, 3 equals x plus 2, x is 1. When this is negative 3 equals x plus 2, x is negative 5. So our 2 x-intercepts right there. Plotting all 3 points that we found. Also, I forgot to plot the y-intercept. Y-intercept, I think, was 0, negative 2. Or no, what was it? 0, negative 10. Right. My bad. All right, so plotting the 4 points that we knew, connect them. There you go. Or you could have also, found the 2 x-intercepts and graphed that way, but then it is good practice to know the y-intercept anyway. So there we go. However, I said we had to convert to general form first. But is that true? The answer is no. Okay, so what we're going to do is this. Instead of converting this to general form, we also know that the vertex occurs at h equals negative b over 2a. ax squared plus bx plus c. Without needing to convert it all, we can find h via calculation. Okay, well, b is 8, a is 2, so 8 over 2 times 2, 2 times 2 is 4, 8 divided by 4 is 2, so the vertex occurs at x equals -2, or h equals -2. But we knew that from the last example. Well, how do we find k, right? We know h. How do we find k in h comma k? Well, that's just plugging in h. So when we plug in -2, 2 times -2 squared plus 8 times -2. All right, -2 squared is +4. Okay, +4, and then 2 times 4 is 8. 8 times -2 is -16. So this is -18. So our vertex is at -2, -18. Y-intercept, we set x equal to 0. So plug in 0 into this standard form. Well, this one's even easier. This term is 0. This term is 0. Whole thing, just -10. So actually, in some ways, standard form could be easier as opposed to general form. X-intercepts, all right, set f of x equal to 0. And all right, well, this requires a little bit more work to solve because it's not in a nice factored version that we could just take the square root of both sides for. However, let's divide both sides by 2, right? All of these have are a multiple of 2. This we can factor, and then we get -5 and 1, just like we got before. All right, and look at that. We had all the exact same points that we had from doing it in general form. Okay, here's -3x squared minus 3x minus 6. So instead of doing this one via general form, let's just go right for keeping it in standard form. Vertex occurs at h equals -b over 2a. So b, ax squared plus bx plus c. B is -3. A is also -3. 2 times -3 is -6. Well, -3 over -6 is 1/2, but the extra negative on the outside makes the vertex occur at -1/2. Well, we don't love fractions. We would have gotten fractions doing it the other way too. So this isn't going to be super pretty, but we can find k by doing f of -1/2. And yeah, I'll trust you guys to do your fraction multiplication and addition. So the vertex is at -1/2, -21 over 4. Y-intercept says set x equal to 0. Okay, well, this is really nice because that's 0, that's 0. So it's just -6, 0, comma, -6. X-intercepts set the whole thing equal to 0. Let's divide everything by -3. And actually, this doesn't have any x-intercepts. So try doing it with quadratic formula, and when you get that, you end up getting 2 complex zeros. So in that case, there are just no x-intercepts. Okay, well, we're given only 2 points, but like I said, now that we only know 2 points, we could take this point, reflect it over the axis of symmetry, 1/2 of a unit to get to here, another 1/2. We would get a, oh, just kidding. This was the vertex. So take this point, reflect it over this axis of symmetry, and you would get this point right here to also be -6. So that's graphing. Some more basics. We're just going to wrap up the section here. The domain of all quadratic functions, there's no point that you could plug in an x and get something undefined. So the domain is all real numbers. The range is dependent on the value of a. So if a is positive, that means your parabola opens up. That means all of your y values are your k to infinity. But if your parabola opens down, then your range is -infinity up to k. Your parabola looks like a cup if a is positive and a hill if it is negative. We saw that in the examples, but it's a good way of checking your work if you know what a is. If your a is bigger than 1, the absolute value of a is bigger than 1, that means your graph gets a little bit sharper, a little bit narrower. But if it's a fraction between 0 and 1, it gets a little wider. And then, just throwing this out there, there's a ton of physics applications when it comes to quadratic functions, right? Physics is very, very broad. However, usually the first chapter of physics when you take a basic physics class is kinematics. Even before kinematics, you might just do, you throw a ball off a cliff, and when does it hit the water? how fast is it hitting the water, stuff like that. And you'll deal with quadratics a ton when you are doing information like that. So just throwing that out there. So that's the end of 3.1. 3.2, we're going to get into in the next section, but that's the end of 3.1. We're just going to go from degree 2 to any degree and talk about all of the information associated with polynomial functions. Okay, so with that said, I will see you in 3.2. Hi, everyone. Welcome back to 3.2. So in 3.1, we talked about quadratic functions. And what we're going to do here in 3.2 is talk about polynomial functions, right? Quadratic functions are degree 2, but what we're going to do here in polynomial functions are for any degree and talk about properties that it can apply to any polynomial. So let's get into some basics. So linear functions are f of x equals mx plus b. Quadratic functions are a times x minus h squared plus k, or ax squared plus bx plus c. So then the general polynomial function for any degree is this messy looking thing right here. However, we've actually seen this before. We looked at this in chapter P when we talked about general polynomials, just the expression polynomials. So not super scary, not kind of familiar, but we'll just go through some of the bullet points about them. So each of these things sitting out in front, for example, a sub n minus 1, a sub n minus 2, we call those all coefficients. Specifically, we want them to be real numbers when we talk about polynomials. Then each of the exponents are referred to as exponents, but we specifically want them to be whole numbers. So the coefficients themselves can be any number we want. However, the exponents have to be whole numbers. If you think all the way back to chapter P, in the case that we had something like x to the 2/3, we didn't even call it a polynomial. We just said it's not a polynomial. So just be careful of that. Each specific thing being added or subtracted together is called a term. And specifically, the one that sits in front is the leading term. Well, that would make the coefficient the leading coefficient. And we say n, that exponent is the degree. Now, specifically, the leading term in any polynomial is the term with the highest degree. And normally we like to write terms in descending power order. We call it standard form. But in the event that your terms are not in descending power order, your leading term is the term with the highest degree. So very quickly, some more basics before we get into the interesting stuff of a section. The domain is all real numbers for all polynomials. There's no number that we can plug in that would make a polynomial undefined. And the range of all odd degree polynomials, well, odd degree polynomials, they go in different directions. So in that case, that would be all real numbers, but the range of all even degree polynomials would be dependent on the leading coefficient and whether or not we have maximums or minimums, kind of like for quadratics. So first thing we're going to talk about in polynomials is end behavior. And this is new information, but you're going to see it's not really all that scary. So the leading term tells us about the end behavior, or specifically how a function behaves as it goes forever to the right or forever to the left. Okay, so start by looking at the degree of the leading coefficient. Okay, if n is even, so squared to the 4th to the 6th, your end behavior is the same as you approach both directions. So kind of think about a parabola, right? X squared, both sides go up, negative x squared, both sides go down. Well, how do we know the difference between both sides go up and both sides go down? That comes down to the leading coefficient. If the leading coefficient is positive, then both sides will go up. If the leading coefficient is negative, then both sides will go down. However, when the degree is even, the end behavior is the same. So when the degree is odd, the end behavior is different as you go in each direction. So kind of think about x cubed in this case. If the leading coefficient is positive, the left end goes down, right end goes up. And if the leading coefficient is negative, then the left end goes up and the right end goes down. So the opposite to what we just talked about. So putting all this information, we actually get this nice little graphic right here that says when our degree is even or odd and the leading coefficient is positive or negative, we get these 4 situations. So notice this kind of looks like x, negative x squared, x cubed, and what would be negative x cubed. So just some more specific graphical examples. We have, x to the 4th minus 2x squared. even degree and positive leading coefficient, even degree and now negative leading coefficient. One thing I want to stress about here too is these little zigzags. Well, these little zigzags say we don't really care what's happening in the middle. Of course, this graphic is only telling us what is happening on the ends, the end behavior. There's x cubed, degree is odd, and leading coefficient is positive. And if we make the leading coefficient negative. So let's do some examples where we determine end behavior. Well, we have 2x cubed plus 5x minus 2. So the first thing we want is the leading term. Well, the leading term in this case, the term with the highest degree, happens to come in the front, which is 2x cubed. Now, what we're interested in terms of degree and leading coefficient is whether or not the degree is even or odd, if the leading coefficient is positive or negative. We don't care about the actual values themselves. We only care about that very general case of even, odd for degree, positive, negative for leading coefficient. So here, the degree is 3, which is odd, and the leading coefficient is 2, which is positive. So now go back to that graphic and look where degree is odd, leading coefficient is positive. It looks like this. Okay, so here's the graph of that. And next up, let's do negative x squared plus x plus 4. The leading term is the term with the highest degree, which again is negative x squared. Okay, the degree, we only care about even, odd. Well, the degree is 2, which is even. For leading coefficient, we only care about positive versus negative. Well, negative x squared is negative. So even and negative, look at that graphic and see what it corresponds to. Even and negative is going to look a lot like this one right here. There's the graph of that function for a little bit more proof. Let's do another one. 1 minus x cubed minus x squared. So the leading term, it's supposed to come to the front. However, notice that our term with the highest power is not in front. That's okay. We can pull it right from here. If it is more comfortable for you to rewrite it with negative x cubed in front, you're very welcome to do that, but you don't necessarily have to. So leading term is negative x cubed. Again, easy way of remembering it is the term with the highest power. Okay, well, the degree, again, just even versus odd. 3 is odd, and the leading coefficient is obviously negative. Odd and negative corresponds to this right here. And the graph of that, a little bit something like that. Okay, 4 plus x to the 4th. Okay, well, leading term is going to be term with the highest power. Again, not actually sitting in the front, but that's okay. It's x to the 4th. The degree is even, and the leading coefficient is positive. Even and positive just looks like x squared. However, what if in the case that we have a function who's not fully expanded and is instead all factored? How do we do this? Well, think about this again. When we're looking for the leading term, we don't care what the values are. We only care about even versus odd, or positive versus negative in the case of leading coefficient. So here's what we're going to do. In the case that this is all factored, we're just going to look at the x terms in each factor. So in this case, if we have 4x raised to the 5th power, we would do 4x minus 5 times 4x minus 5 times 4x minus 5 times 4x minus 5 times 4x minus 5, but that's a lot of work. So instead, just take this 4x and raise it to the 5th power. Well, 4x to the 5th, you would get an x to the 5th term at some point in there. And same thing here, you would do 2x plus 1 times 2x plus 1, but at some point you would be doing 2x squared, which would give you 2x's. So nice easy way of looking at this is we have 5x's here, 2x's here. In total, we have 7x's. Well, we know what the degree is now. It's x to the 7th, but what is the leading coefficient? Well, let's do the exact same thing, but now look at the coefficients of each of these x's. Well, this coefficient is positive. Raise it to the 5th power, still positive. This leading coefficient is positive. Raise it to the 2nd power, it's still positive. This positive leading coefficient times this positive leading coefficient will be positive. So the degree is 7, which is odd. the leading coefficient is, we just said is positive. Odd and positive looks like this. Next up, 3x minus 6 cubed times 2 minus x to the fifth. All right, well, same thing. To get the leading term, let's take a look at our x terms and see what happens. Well, we have an x here. We raise it to the third. We have 3 x's. Here we have an x and 5 of them. So in total, we have 3 x's plus 5 x's. We have 8 x's. So we know what the degree is. The degree is 8. But what's the leading coefficient? Okay, well, here we have 3 raise it to the third power. That's positive. Here we have negative x, though. Ooh, be very careful. The sign of our x is negative. So a negative x raised to the fifth power will still be negative at the end. So in total, positive times a negative would be a negative leading coefficient. So negative and even would be this one right here. Okay. Let's do that again, but just slightly change it so that it's x to the fourth here. Well, notice that we can just add the exponents to figure out how many x's we have, right? X cubed, x to the fourth, we have 7 x's. But now we need to determine what that leading coefficient is. Well, 3 cubed is still positive, but now we have negative x to the fourth. Well, negative x to the fourth is then positive. So we have a positive times a positive in this case. So we have a positive leading coefficient. Okay, the degree is odd. Leading coefficient is positive, again, because negative x to the fourth will be positive, not negative anymore. Odd and positive right there. Okay, we can make it one step funkier to do x squared here. Only thing that changes is when we are going to count how many x's we have. Well, this is x squared to the fifth power. So here we actually have 10 x's. You would do x squared times x squared times x squared times x squared times x squared, but each of those x's was 2 of them. Sorry, I'm doing like a John Cena thing here. So we would have 10 x's in total. So we have x to the 10 times x squared. So in total, we have 12 x's, 4 is positive, 2 is positive, positive. Okay, even degree, positive leading coefficient, we get this bad guy right here. So that's end behavior. Well, next thing we're going to talk about are zeros. Now, zeros are actually really, really nice because we've been doing stuff like this forever. We're just going to start to give these things names in this subsection and in the next subsection. So zeros of a function are the values, the x value specifically, where your function equals, you guessed it, 0 for talking about zeros, right? But the locations where f of x is 0, we had a definition for that. That is the x-intercepts. Oh, we've been finding intercepts almost entirely in chapter 2. So here in chapter 3, we're doing the same thing, except now we're going to give these things some new names. So suppose that c is our 0. Suppose c satisfies f of x equals 0, then all of these following statements are true. C is a 0 of f of x. Okay. C is a solution to f of x equals 0. Also okay. C is an x-intercept of f of x. Okay, that also makes sense. And then last is x minus c is a factor of f of x. Now, we know what factors are, but we're going to talk a little bit more about how this is possible in the next section, sort of see how important this is in 2 sections in 3.4 and 3.5. So we're going to put this one on the back burner for right now, but essentially, in terms of nomenclature, 0, solution, and x-intercept all mean the exact same thing. So another interesting thing that we want to keep some foresight out for is a degree n polynomial has at most n real zeros. Okay, we're going to think about that. But again, it'll be a little bit more important in 3.4 and 5. All right, find the zeros of 5, x minus 4, x minus 3, x plus 1. Well, to find the zeros, we got to set this thing equal to 0. So let's take each factor and set them all equal to 0, right? Exactly like how we solved equations in the past. If we have 4 things being multiplied to 0, well, at least one of them has to be 0. There's no way that all 4 of these could be non-zero and allow them to multiply to 0. Okay, Well, 5 doesn't equal 0. X minus 4 equals 0 at x equals 4. Just add 4 to both sides, then add 3 to both sides, then subtract 1 on both sides. So we have 3 zeros. -1, 3, and 4. Okay, let's do it again. This one we're going to have to do a little bit of work because this isn't perfectly factored for us. So we want to find its zeros. Let's start by taking out an x, and then the inside of that parentheses can factor to x plus 2 times x plus 1. Okay, well, now if we want to find the zeros, set it equal to 0, and just like the last example, set each specific thing equal to 0. Well, x equals 0 is just x equals 0. Then we get -2 and -1 when we subtract 2 and subtract 1 respectively. So we get 3 zeros, -2, -1, and 0. Okay. Well, here's something interesting. We said before a degree 3 polynomial would have at most 3 real zeros, right? A degree n polynomial has at most n real zeros. So this degree polynomial has 3 zeros. Okay. Let's do it again. X to the fourth minus 2x cubed minus 3x squared. Let's find the zeros. We got to start by taking out an x squared. Then we can factor. Then we can set it equal to 0. Let's set each factor equal to 0. X squared equals 0. That's just x equals 0. Then x equals 3. Then x equals -1. So our zeros are -1, 0, and 3. But this degree 4 polynomial has only 3 zeros. Well, that's kind of weird. Well, I mean, that fits the statement we made earlier that a degree n polynomial has at most n real zeros, but you would think that it would have 4. I wonder why. Okay, x cubed minus 2x squared plus x minus 2. We can factor by grouping. All right, we get x minus 2 times x squared plus 1, and we'll set that equal to 0. Set each of those two things equal to 0. For the first one, we get x equals 2. But for the second one, well, x squared plus 1 equals 0 is never true, right? You could subtract 1 on both sides, and then you get x squared equals -1. Then you take the square root of both sides, you get square root of -1, which we know isn't real. Well, that's one way you could think about it. You can also think about it that x squared equals -1. Well, take any number and square it, it's positive, so that can't be true. But also, take a positive number, square it, it's positive. Plus 1, still positive, not 0. Take a negative number and square it. Well, negative squared is positive. Positive plus 1 is still positive. Okay. Well, 0 squared is 0, but 0 plus 1 is also not equal to 0. So this one never equal to 0. That means x equals 2 is our only 0, and that's okay. However, a degree 3 polynomial has only 1 0. Weird. X to the fourth minus 16. Alrighty, we can factor this using difference of squares twice and set it equal to 0. Let's set each factor equal to 0. Well, first one we just saw wouldn't work. If x squared plus 1 never equals 0, x squared plus 4 definitely is never going to equal 0 either. Subtract 2, add 2, so we get 2 zeros. But again, this was a degree 4 polynomial, and it only has 2 zeros. That's pretty weird. Okay, well, that brings us to multiplicity, which is going to help us start to explain why we had some mismatches in our degrees and our zeros. Well, let's do the same question, but let's do x minus 1 cubed. Well, x minus 1 cubed is x minus 1 times x minus 1 times x minus 1 equals 0. So what we're going to do is set each factor equal to 0, but we get 1, and we get 1, and we get 1. So x equals 1 is the only 0, and this degree 3 polynomial has only 1 0, but that 1 0 happened 3 times. Maybe there's something about that. Well, it happens to be called multiplicity. So the multiplicity of a 0 is simply the number of times a 0 appears in your function. So in the very last example, normally if we're just solving the equation x minus 1 cubed equals 0, well, you would just take the cube root of both sides, add 1, and you're done. But now what we're going to start to say is that x minus 1 cubed equals 0 says that x equals 1 has a multiplicity of 3. So you could say has multiplicity 3 with multiplicity 3. I believe I use with everywhere that we talk about multiplicity, but has with, same thing. So it's not just x equals 1, it's x equals 1 with multiplicity 3 in the context of finding zeros. So x plus 2 to the 5th equals 0. Before, we would just say that x equals -2, but what we can now say is that x equals -2 with multiplicity 5. Multiplicity being just the exponent. All right, well, the interesting thing about multiplicity is that graphically, it helps us determine whether or not your function crosses the x-axis or touches the x-axis at that 0. So let's say you have some function and it works its way down to a 0. Well, the multiplicity of a 0 determines whether or not that function just touches it, it comes back up, or crosses through that 0. If a 0 has odd multiplicity, then the graph of your function crosses the x-axis at that 0. But if a 0 has even multiplicity, then the graph of f of x just touches and does not cross the x-axis at that 0. Okay, and then just one thing to note is that when I've taught this in the past, I've been told bounces is a good way of thinking about it. So yes, it touches and doesn't cross, but you can also think about it as it hits the x-axis and then bounces back up or bounces back down. That's another good way of thinking about it. We'll come back to this in a little bit. So let's just practice finding zeros and their multiplicities. Well, redoing some of the examples we just had, well, here, this was the answer that we got for this function, but what's the multiplicity of each 0? Well, x equals -1 appeared only one time, x equals 3 only appeared one time, and x equals 4 only appeared one time. So all three zeros multiplicity is 1. Here we go, same thing. This is what we got before. -2 appeared only once, -1 appeared only once, and 0 appeared only once. Okay, one more time. Here we have -1, -1 appeared only once, but for the first time, notice that where we got x equals 0 from happened twice. So x equals 0 would have multiplicity 2. If this was x cubed, it would be x equals 0 multiplicity 3, x to the 200, x equals 0 multiplicity 200, and so on. X equals 3, well, this one, there's an imaginary 1 exponent up here, so multiplicity 1. So usually exponents really helpful for us to figure that out. So this time, there's only 3 zeros. That part hasn't changed, right? The problem we had before was that we had 3 zeros degree 4, but the multiplicities all add to 4. That helps us explain where the missing 0 went. Well, it was really just hidden behind a multiplicity. All right, well, here, this function, degree 3, we got only 1 0, and that 1 0 still only has multiplicity 1. So we're still degree 3, and we still only have 1 0. Maybe there's another explanation to that. That'll come in a couple sections. X to the 4th minus 16. Well, x equals -2 and 2. X equals -2 appeared only once. X equals +2 appeared only once. But then same thing. This is degree 4, and we still only have 2 zeros. We're going to have to come back to that. Okay, let's do some brand new examples. X minus 1, x plus 2, x minus 3. Just go through and set each factor equal to 0. Well, first one, we get x equals +1 when you set this equal to 0. And this 0 appears only one time. The next one we would get is x equals -2 with multiplicity 1. And then we get x equals +3 with multiplicity 1. Okay. 2x plus 1 to the 4th times x minus 36 squared. All right, I'm going to trust you guys to set each factor equal to 0. So set this equal to 0 and solve it. You would subtract 1 on both sides, then divide both sides by 2, which would give us -1/2. And this multiplicity is 4. Okay, for the next one, a little bit easier. We're going to add 36 to both sides. So we get x equals +36 multiplicity 2. Okay, let's do this one. X plus 6 to the 7th times 2x minus 3 times x minus 4 cubed. All right, first one, we get x equals negative 6, multiplicity 7. 2x minus 3, set this equal to 0. Add 3 to both sides, divide both sides by 2. We get 3 halves, multiplicity, whatever this exponent is, 1. X minus 4 would give us x equals positive 4, multiplicity 3. All right, let's do a horrible example. X to the 32,123, 4x minus 100 to the 200, 10x plus 1,000 to the 633. Well, first factor, x to the 32,123, x equals 0 with multiplicity, whatever that exponent is. 4x minus 100 here, add 100 to both sides, divide by 4, you get 25, multiplicity 200. And last but not least, 10x plus 1,000, subtract 1,000 on both sides, divide both sides by 10, we get negative 100, multiplicity 633. I do not recommend graphing this function, but there we go. Okay, well, let's take this jumbled mess and find its zeros and multiplicities. So in order, we would get negative 1, 6, 2, negative 1, negative 1, 4. Okay, 2x plus 4. Subtract 4 on both sides, divide by 2, we get negative 2. Add 4 to both sides, divide by 2, we get positive 2. So in total, x equals negative 1 appeared 3 times. X equals 6 appeared 1 time. X equals 2 appeared twice. X equals 4 appeared once. And last but not least, x equals negative 2 appeared once. Okay, one more weird example. X squared minus 9 to the 4th. Okay, x squared minus 9 is x plus 3x minus 3. Since x plus 3 times x minus 3, they're multiplied together, we can distribute 4. So we get x equals negative 3, multiplicity 4, and x equals positive 3, multiplicity 4. So multiplicity, really just taking into account degrees. Well, before we actually use zeros and multiplicities, I just want to talk about one very, very quick theorem, and then we'll come back to that for one example in graphing. So that's intermediate value theorem. Now, intermediate value theorem is this very wordy definition right here, but let me use temperature to explain what's happening. So think about it this way. Let's say you wake up at 8 a.m. and it is 40 degrees outside. Then at noon, you check the temperature and it is 60 degrees outside. So in 4 hours, the temperature went from 40 degrees to 60 degrees. And then I ask you, was it 50 degrees at any point between 8 a.m. and 12 p.m.? Well, yeah. It might not have been for long, but temperature doesn't work in such a way that it's like it's 40 degrees now, and then all of a sudden it's 60 degrees 5 minutes later. I mean, it can do that, right? It can heat up very quickly, or it can cool down very quickly. Maybe not 5 minutes quickly, but it can do that. But the point is that it doesn't just immediately jump from 40 to 60. What temperature has to do is go from 40 to 41 to 42 to 43, and even smaller than that, right? 43.1, 43.2, 43.3, 43.31, 43.32, and so on. It has to hit all of the temperatures up to 60 degrees. Now, it might not be for a very long time that it hits that temperature, right? It could be 43 degrees for maybe, 15 seconds, but the point is it does hit every temperature. So my question to you asking, was it 50 degrees at any point? Yes. If it was 40 before and it's 60 now, even if it was for an instant, it had to be 50 degrees at least once. However, what if I asked, was it 20 degrees at any point? Well, that's not guaranteed. If it started at 40 and ended at 60, it is totally possible the temperature dipped and then all of a sudden shot back up. But that's not a guarantee. That's a very specific scenario where it does that. So we can't say confidently that it did happen because, that's very unlikely. But we also can't say that it didn't happen because even though it's unlikely, it's still possible. So with that said, intermediate value theorem just says, depending on what your endpoints are, every value in between those values of the endpoints is guaranteed to have happened. So how we contextualize this to what we've been talking about is that essentially, let's say you have some function on some interval from A to B. If one of your endpoints values is positive when you plug it in, and one of the endpoints when you plug it in is negative, well, if one is positive, one is negative, at some point you had to cross 0. And that's going to be the important part to this section. So all we need to do is show that one value is positive, one value is negative. There's no way we can go from negative to positive without crossing 0 at some point. And that's what we're interested in. So what we're going to do is, for these examples, plug in the endpoints and see what we get. If the signs differ, then we do guarantee that there was a 0. If they don't, we can't necessarily guarantee that. Okay, so f of x equals negative 2x cubed plus 4x plus 5 from 1 to 2. Well, let's just plug in the endpoints. So when we plug in 1 cubed is 1, negative 2 times 1 is negative 2, 4 times 1 is 4, negative 2 plus 4 plus 5 is 7. Okay, likewise, let's do the same thing for the other endpoint. All right, for the other endpoint, 2 cubed is 8, negative 2 times 8 is negative 16, 4 times 2 is 8. Well, negative 16 plus 8 is negative 8. Negative 8 plus 5 is negative 3. So we started at 7 and we ended at negative 3. Did we cross 0 at some point? Yes, we had to. There's no way we can go from 7 magically down to negative 3 without crossing 0. So now we don't necessarily care where it happened. All intermediate value theorem says is that we guarantee it to happen. So that's kind of interesting. It's kind of a funny glimpse into mathematics that in some cases we don't even necessarily care what the value is. Like, we're saying that there is a spot that it crosses the x-axis, but we don't really care what it is. You can solve it, but we don't care. We just care that it does exist at some point. And that does actually kind of happen. The higher up in math you go, that at some point we stop caring what the answer is and just say, there is an answer. That's good enough. Okay, let's do the same thing for x cubed minus 5x squared plus 6x minus 6 from 1 to 2. All right, so let's plug in each of our endpoints. 1 cubed is 1, 1 squared is 1, 5 times 1 is 5, 6 times 1 is 6. 1 minus 5 is negative 4. Negative 4 plus 6 is 2, but minus 6 again, we're back to negative 4. Plug in 2. All right, 2 cubed is 8, 2 squared is 4, 5 times 4 is 20, 6 times 2 is 12. 8 minus 20 is negative 12. Negative 12 plus 12 is 0. 0 minus 6 is negative 6. So we started negative and we ended negative. Is there necessarily a 0 between 1 and 2? Well, we can't guarantee that. It is entirely possible that if we started at negative 4, ended at negative 6, that we go up very quickly and down very quickly, but we can't guarantee that's what happened. It might have happened, but we can't guarantee it. So that's the important part. Okay, let's do the same thing, but with 3 and 4 instead. Plugging in 3, 3 cubed is 27, 3 squared is 9, 5 times 9 is 45, 6 times 3 is 18, 27 minus 45, negative 18, negative 18 plus 18, 0, 0 minus 6, negative 6. Okay, same thing for the other endpoint. 4 cubed is 64, 4 squared is 16, 5 times 16 is 80, 6 times 4 is 24. 64 minus 80 is negative 16, negative 16 plus 24 is 8, 8 minus 6 is 2. Is there a 0 between negative 6 and 2? There sure is. Has to be. So that's intermediate value theorem. Now, to end off polynomial functions, this very large section, right? It's very interesting because even at this very low level of mathematics, we're able to sketch graphs. They might not be very good sketches, and there's one really key part that we're missing that I'll point out when we do an example. But yeah, with everything that we talked about in this section and everything we've talked about in the past, we can actually graph. We can at least sketch graphs. So the steps to do that are as follows. Determine the end behavior using the leading term. That's what we did for the first few examples of this section. Next up, find the y-intercept by setting x to 0. Find the zeros and their multiplicities by setting the whole function equal to 0. And here's the weird new step. Once we find the zeros, we're going to take those zeros and partition the domain. Very fancy phraseology. All it's saying is put your zeros on a number line. When you put those zeros on a number line, what you create is separated intervals. What we're going to do is check a value in each of those intervals to determine whether or not our function is above the x-axis or below the x-axis. After we know that, we can sketch the graph. And in general, I kind of mentioned it in the last section too, but if we are dealing with degree n, you should use n+1 points. So if you are trying to graph something that is x cubed, you should have 4 points officially graphed. So I'm going to do one example of this. It's a very long section. I don't want to stretch it out any further. But let's do one example of this, and then we'll call it a day. So I will see you on the whiteboard. Okay, I know how much we love the whiteboard. So here's our function, x times x plus 2 cubed times x minus 1 squared. Okay, so step 1 says find the end behavior. So we need the leading term for that. Okay, leading term says how many x's do we have? We have 1, 3, right, because of the 3. And here we have 2. So in total, we have 1 plus 3 is 4. 4 plus 2 is 6. And now we care about the leading coefficient. The leading coefficient of this x is positive. This x is positive. This x is positive. Multiply a bunch of positive numbers together, you get positive. So when we have positive and even, this corresponds to something that looks like that on our original little graphic of all 4 cases. So there we go. Well, now we can find the y-intercept by setting x equal to 0. So f of 0 is 0, 0 plus 2 cubed, 0 minus 1 squared, but the 0 out in front, whole thing is just 0. So our y-intercept is 0, 0. Next up, zeros and their multiplicity. So we're going to do whole function equal to 0. Well, we get x equals 0, x plus 2 cubed equals 0, x minus 1 squared equals 0. So we get x equals 0, multiplicity 1, x equals negative 2, multiplicity 3, and x equals 1, multiplicity 2. Okay, so here's the weird new step. What we're going to do is take these zeros and put them on a number line. So we have negative 2, 0, and 1. And what we're going to do is check to see whether or not our function is above or below the x-axis on each of these 1, 2, 3, 4 intervals. Now, what we could do is what we're supposed to do is take a value in each interval. So say negative 3, negative 1, 1/2, and 2. Plug those into the original function and see if we're positive or negative. But that's actually a little bit more work than we really need to do because we found the end behavior and we found the multiplicities. Well, our original end behavior told us that both sides are going to go up. Both ends are going to go up. So we know right away, left side goes to positive infinity, right side goes to positive infinity. Well, in that case, it has to go up. It has to be above the x-axis. Okay, so now what we're going to do is determine what happens at each of the zeros. Don't forget, multiplicities told us whether or not our function crosses the x-axis at that 0 or touches the x-axis at that 0. So odd multiplicities cross, but even touches, or some people also like to say bounces. So we start above the x-axis at -2, and then at -2, we have odd multiplicity. So odd multiplicity means that we will cross into negative territory. So we went from plus to minus, right? We crossed at -2. Okay, so at some point, we come back up and we get up to 0. And at 0, we again have odd multiplicity. So we're negative and we cross at 0 into plus. At some point, we come back down and then we come back down to 1. But 1 has even multiplicity. Even multiplicity means it'll just touch, but not cross, and it goes back up. So it kind of bounces. That's where this like bounces idea comes from. Okay, so we know when our function is above and below the x-axis, but now let's graph this. Let's put our zeros where we just found them. We said the function is above the x-axis. At -2, it crosses into negative. At 0, it crosses back into positive. And at and at 1, it bounces back up to positive. Also, one thing I'll note is that even though we knew this end behavior was plus, we could still have checked it with this bounce. So you didn't necessarily need to check this last spot because we already knew it via the end behavior, but you know what? Still good practice to see why. So this nice rough sketch of our graph. So the big thing here is that, one, we could be more precise by actually plugging in values, right? Say we plugged in -1. What's the value here? Say we plugged in 1/2. What's the value here? The other problem, too, is notice this is a minimum and this is a maximum. The question is, where exactly does it start to come back down? Where exactly does it start to go back up? Right? I said at some point we start to go back up. And the question is, well, what's that some point? Well, here's the thing. We can't answer that right now. We technically need calculus 1 to be able to answer that question. So can't do it right now. That's not a big deal. But for very little algebra we have under our belt, it is cool that we're able to graph functions as clearly as this. So that's the end of 3.2. In 3.3, we're going to completely change gears. There's a little surprise. In 3.3, you'll see it right away, but then we'll come back to the normal format in 3.4. So I will see you in 3.3. Bye.
Hi everyone, welcome to section 3.3 where we do polynomial long division. To this point we've talked about zeros, we've talked about factors plenty of times. So what we're going to do in this section is if we have the opportunity to divide by a factor that would help us divide and then factor some more, we would like to take that opportunity, right? So what we're going to do is take some really big polynomials, try and divide them by certain factors, and if we divide them by factors, they might be factorable. So for example, we could potentially go from something that's like x to the 4th that we can't factor, but if we divide by a certain factor and it works, then maybe we have something with x cubed, and then we can then factor from there. So it is a popular tool. It's a very famous tool. There's 2 ways we're going to do it. So yeah, let's get right into it. So how we're going to do this is a lot like how we did this for numbers. So think about when you were in elementary school and you did something like 830 divided by 5. Well, you would set this up as 830 over 5, and then you would say 5 into 8 one time. You would do 1 times 5, which is 5. 8 minus 5 is 3. Then you would bring down the next number. 5 into 33 6 times. 6 times 5 is 30. Bring down the 3. And then we get 5 into 30 6 times. And that's 0. So we say this is 166. But another way we could say this is that 830 is 5 times 166. So that kind of ideology is going to carry us for these first few examples. So let's do just that with polynomials. Okay, so the first example we're going to do is x cubed plus 2x squared minus 5x minus 6 all over x plus 1. Okay, so how we set this up is a lot like how we set this up for numbers. We would say x cubed plus 2x squared minus 5x minus 6 divided by x plus 1. Okay, but how we do this is a little different. When we do it for numbers, we're used to saying 5 into 8 one time, but it's not that easy because we have an addition here or even a subtraction. So what we're going to do is this. We're going to ask how many times does this first term go into each consecutive, or successive I should say, term. And what I mean by that is how many times does x go into x cubed? What I'm really asking is what is x cubed divided by x? X into x cubed is saying x cubed divided by x, which is x squared. So what we're going to do with x squared is line it up with the other x squared terms, right? We want to make sure we're lined up, just like we're lined up for tens, hundreds, thousands when it comes to dividing numbers. And what we're now going to do is the same step as we did for numbers. When we said 5 into 8 one time, we would then say 1 times 5 is 5. And we're going to do the same thing here. X squared times x plus 1, okay? X squared times x cubed. X squared times 1, x squared, okay? And now we subtract. So it's a little different because we're not subtracting just single numbers. This time we're subtracting expressions, and that's a-okay. If we did this correctly, these two things should be the same. This says x cubed minus x cubed. Oh, well, that goes away. That's pretty nice. But then this says 2x squared minus positive x squared. Well, 2x squared minus positive x squared is just x squared, right? 2 apples, you subtract one of those apples, you now have 2 apples. Okay, and then, just like we did for numbers, bring down the next term. Okay, and now we rinse and repeat. So now we ask, how many times does x go into x squared? Or in other words, what is x squared divided by x? And that's just x. So now we put x up here, and we again do x times both of these. X times x is x squared. X times 1 is x. But now we got to be a little more careful. Again, if we did this correctly, x squared minus x squared, that's just 0. But here we have negative 5x minus positive 1. You're $5 in debt and you spend one more dollar. You now have negative $6 of debt. Okay, bring down the next term. And now one more time, x into negative 6x. Negative 6x divided by x is negative 6. All right, and one more time. Negative 6 times x, negative 6x, negative 6 times 1, negative 6. And in this specific case, this is pretty nice. Negative 6x minus itself goes away. Negative 6 minus itself goes away. We're left with 0. So now, our original question asking, what is x cubed plus 2x squared minus 5x minus 6 divided by x plus 1? Well, this equals x squared plus x minus 6, okay? X cubed plus 2x squared minus 5x minus 6 over x plus 1. Well, what we can do like we did with numbers where we said 830 divided by 5 is 166, we can multiply x plus 1 on both sides. And even better yet, this factors to x plus 3, x minus 2. So what polynomial division did is that if we find a factor that is indeed a factor of our original polynomial, just like 5 is a factor of 830, if we find one of these that works, well, it lowers our degree of our polynomial to a point that we could potentially factor it. So this, before, you would never have been able to factor using regular means, but just like that, with one run of polynomial division, now it is factorable. And that's the idea. Okay, let's keep going. Let's do some more examples. Okay, so next up, we're going to do x to the fourth minus 26x squared plus 25 divided by x minus 5. So what we're going to do here, same thing, let's set it up. X to the fourth minus 26x squared plus 25 over x minus 5. And now what we're going to do is say x into x to the fourth. X to the fourth over x is x cubed. And, well, that's kind of weird because we don't have a spot for x cubed. Well, whatever, let's throw it up here for right now. Now we do x cubed times all this. So x cubed times x is x to the fourth. X cubed times negative 5 is negative 5x cubed. And just like that, all of our terms are out of whack. Notice this is x squared, this is x cubed. We can't subtract like that. So what we're instead going to do is put placeholders in for all of these powers of x that we're missing. So this is a bad setup. And again, if you are missing powers of x, what you instead need to do is this. Okay, x to the fourth, next term is negative 26x squared, but since we're missing an x cubed term, let's put 0x cubed there. Minus 26x squared. We're missing an x term, so let's put 0x there, plus 25. Okay, so same thing, x into x to the fourth, x cubed times x to the fourth, x cubed times negative 5, negative 5x cubed, and now we have less of an issue because we have x cubed terms that line up. However, be very careful here because what we're doing is x to the fourth minus x to the fourth. That's the whole point, it goes away. But here, 0x cubed minus negative 5x cubed. Well, this is plus. So this is positive 5x cubed. So please be very careful when you are subtracting. Don't forget parentheses. If you forget parentheses, you're going to just subtract here, and this will be negative, and then you're going to be all sorts of thrown off. Okay, so please be very careful of that. We continue, minus 26x squared, x into 5x cubed is 5x squared, 5x squared times x, 5x cubed, 5x squared times negative 5, negative 25x squared. Okay, those are the same. But over here, careful, negative 26x squared minus negative 25x squared. Well, negative 26x squared minus negative 25x squared is plus. You're $26 in debt and you're given $25. You are now just a single dollar in debt. And we bring down the next term. Okay, x into negative x squared is negative x, right? Don't forget each of these steps. 5x cubed divided by x, that's how we get the 5x squared. Right here, negative x squared divided by x is how we get negative x. All right, negative x times x, negative x squared. Negative x times negative 5, ooh, positive 5x. All right, those are the same. 0 minus positive 5 this time. Okay, you have nothing in your bank account and you spend $5. Now, negative 5x again. One more time. X into negative 5x. Negative 5x divided by x is negative 5. Negative 5 times x, negative 5x. Negative 5 times negative 5 is positive 25, and both of these are the same. And we found a factor. So this original polynomial is equal to x minus 5 times all of that. And if you wanted to, this can be factored by grouping, and you can continue to factor this polynomial. So that's a really nice powerful tool. This could have actually been factored in the beginning if you have a little bit of foresight, but let's assume we don't know how to do that and instead use division. Okay, let's move to something a little different now. So both of these examples worked, but we know in division that that's not always going to be the case. So what happens when something doesn't work? Okay, so in terms of numbers, what if we did 830 divided by 7? Okay, 830 divided by 7 would be 830, 7. 7 goes into 8 one time. 1 times 7 is 7. 8 minus 7 is 1. Bring down 3. 7 into 13 one time. 1 times 7 is 7. Bring down 6, and we get 0. 7 into 60 8 times. 8 times 7 is 56. 4. Well, 7 doesn't go into 4, so what you are used to doing in elementary school is to say 118 remainder 4. Well, here's what 118 remainder 4 actually means. What this means is if you were to divide 830 divided by 7, you would have 118 sevens plus 4 of the way to 7. You go around 118 times, and then you get 4 more steps to your next 7. Well, this is how you would write this. Plug this into your calculator, is the same thing as this. So what we're going to do in the next couple examples is look at the possibility when what we're dividing by isn't a perfect factor. In this case, it's a little weird, but we're going to write our answer something like this. Quotient plus remainder divided by divisor. I'll put that up here. Quotient plus remainder divided by divisor. Okay, so let's do another example, but this time, let's do an example that doesn't work. Okay, let's do x cubed minus 3x squared minus 6x plus 8 all over x minus 3. Okay, so we're going to set this up as x minus 3, x cubed minus 3x squared minus 6x plus 8. And now we rinse and repeat. X into x cubed, x squared. X squared times x squared times x is x cubed, x squared times -3, -3x squared. Okay? And by chance, these both happen to cancel out. That doesn't mean anything's wrong. It just means that's what happened. So we get 0, and we bring down minus 6x. And let's also bring down 8 for when we go to subtract later on. Okay, x into -6x. -6x over x is -6. Just -6, right? Not -6x. So that's okay. It just means that we skip over an x term. There's nothing wrong with that. Now, -6 times x. -6 times x is -6x. -6 times -3, positive 18. Okay, these two are the same. Here we get 8 minus 18. That's -10. And of course, x minus 3 can't go into -10. So here's what our answer actually says. Our answer then says this division is the quotient plus the remainder divided by the divisor. Or if you want to be more particular, minus 10 over x minus 3. This is the same as that 118 plus 4 over 7. Quotient plus remainder divided by the divisor, 830 over 7. So just because something doesn't work out doesn't mean anything's wrong. It just means it means something else. In the case of polynomials, this has use, but in terms of factoring like we were trying to do before, it doesn't quite work out that way. However, this is still of interest to us. Okay, so let's then do another example that maybe also doesn't work, but that's okay. Okay, now let's do something funky like x to the 4th minus 16 over x minus 1. Okay, actually we're going to do x plus 1 instead because why not? Okay, so when we go to set this up, we have x to the 4th, but we're missing an x cubed term, we're missing an x squared term, we're missing an x term, but we finally have our constant term. Okay, so again, if you're missing terms like here, you're missing x cubed, you're missing x squared, you're missing x, make sure you put placeholders in. Okay, so here's what we're going to do next. X into x to the 4th is x cubed times x to the 4th, x cubed times 1, positive x cubed. X to the 4th minus itself, 0 x cubed minus 1x cubed, negative 1 x cubed, and bring down the next term. Okay, x into negative 1 x cubed is negative 1 x squared. And then, again, if you haven't seen it by now, it's just rinse and repeat. Negative x squared times x, negative x cubed, negative x squared times 1, negative x squared. Okay, so negative 1x cubed minus negative 1x cubed goes away. 0 x squared minus negative x squared. Negative is a plus. Just x squared, and we keep going. Alrighty, x into x squared, just x. X into x plus 1, x squared, x times x is x squared, x times 1 is just x. X squared minus x squared goes away. 0 minus positive 1, negative x, and bring down our last term. Okay, x into negative x. Negative x divided by x is negative 1. Negative 1 times x, negative x. Negative 1 times negative 1 is negative 1. Negative x minus itself goes away. Negative 16 minus negative 1. You're $16 in debt and somebody gives you $1. You are now only $15 in debt. Okay, so that means our original question is x cubed minus x squared plus x minus 1 quotient plus the remainder divided by the divisor. And again, you could be a little bit more specific by saying just minus 15 over x plus 1. But I think at this point, if you're watching a video about polynomial long division, I think that part is fairly okay. All right, so this is called long division, and in a lot of ways, this can be very tedious, and it's very easy to make mistakes. So there does exist another type of division when it comes to polynomials that is actually pretty nice. So we're going to do that next. However, I just want to talk about one small thing. Let's say you're trying to divide by something that is more than just like x plus 1 or x minus 5. Let's say you have some polynomial and you're trying to divide it by x squared plus 2x plus 1. So when you go to set this up, x squared plus 2x plus 1 divided by whatever your polynomial is, well, before we had just those two terms, and you said x into whatever that first thing was or whatever that next thing was. In the event that you have x squared, nothing changes. Now it's 3 terms, now it's going to be a little more work. However, you're still just doing this first term into whatever's next. So let's say we start with an x to the 5th here. Well, then you would have, so whatever, plus, I don't know, 2x to the 4th minus 6x cubed and so on. Okay, x squared into x to the 5th. X to the 5th over x squared is x cubed. Okay? And now the only added difference is when you are multiplying x cubed, is that you have to multiply it by all 3. X cubed times x squared, x to the 5th, x cubed times 2x, 2x to the 4th, that is completely by chance, x cubed plus 1, plus x cubed, and now x to the 5th minus itself, 2x to the 4th minus itself, negative 6x cubed minus 1x cubed, negative 7x cubed, and whatever, you bring the next thing down, and you would continuously use x squared. So all I'm trying to show is that in the event you're dividing by something that is higher than just x, that's fine. This x squared or x cubed or whatever it is will just be your new leading term to divide by. Okay, also, just like we put placeholders in for the numerators, right? X to the 4th minus 16, we had to do x to the 4th plus 0x cubed plus 0x squared plus 0x minus 16. In the event you're dividing by something like x squared minus 5, well, you have the x squared term, but you're missing an x term in your divisor, so you still put a placeholder just there. So the examples work very similarly when they're just x, compared to x squared, but the same rules of take this leading term, put it into each and every thing, putting placeholders, all those rules are still the same. Okay, so since we have now talked about that, let's move to this other type of division. It is, I will say, not a very mathy way of doing long division, and if I'm being honest, I didn't really get it the first time that I learned it a long time ago, but as I've been teaching, it makes a lot more sense. However, not very mathematical, not very algebraic, but if you're looking for a very quick way to do long division, it's really nice. So this is called synthetic division, and synthetic division is only for when you're doing division with linear factors. So for example, we've done dividing by x plus 1, x minus 5, x minus 3. You can do synthetic division on those factors. But these last two examples that we just did with an x squared, synthetic division can't work. Synthetic division is only for dividing by linear factors. Okay, so let's go back to this example, x cubed plus 2x squared minus 5x minus 6 over x plus 1. I don't remember what our answer is, but it's okay. We'll match it up with whatever we get. Synthetic division works like this. We're going to set up this little bar here. I don't even know what to call it. So what we're going to do is have a row of numbers up here, and we're going to continuously do calculations below them. Okay, let's start with this. The numbers that go on the inside of our bar will be the coefficients to each of these x's. So x cubed, coefficient is 1. 2x squared, coefficient is 2. Negative 5x, coefficient is negative 5. Negative 6, it is just itself. Okay, that's pretty straightforward, I think. Okay, and then what we're going to put out here is the 0 to our linear factor. So we're not going to put x plus 1 here. We're going to put negative 1 out here. Okay, that is really important here. This is not the number itself. It's the 0 associated with this number. At some point, you've probably talked about zeros already in your classes when you talked about polynomials, and that's what we're talking about when it comes to zeros. It is not x plus 1. It is the 0 associated with x plus 1, in this case, negative 1. Okay, so how synthetic division works is like this. First step, bring down the first number. Okay, not super scary. What we're going to do is continuously work up, down, up, down, up, down. Okay, to get to here, we are going to take our 0 and multiply it by this number. Negative 1 times 1 is negative 1. Okay, so it's multiplication to get back up. But then when we go down, so now 2 and negative 1, when we go down, we add. So diagonals are multiplication, but the columns are addition. 2 plus negative 1 is positive 1. And now negative 1 times 1 is negative 1. Again, negative 1 times 1, negative 1. Okay, negative 5 plus negative 1, negative 5 plus negative 1. Okay, $5 in debt, and you spend another $1, you are now $6 in debt. Negative 1 times negative 6 is positive 6. Negative 6 plus 6 is 0. So multiplication, 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 addition, addition, addition. So here's what we get. We now have a row of numbers and we have no idea what they mean. So what this says is that if this was x cubed and we divided all of these terms by a single x, x cubed divided by x would become x squared. X squared divided by x would become x. Negative 5x divided by x would be a constant. And that would leave this last number to be our remainder. And we remember from when we did this example earlier, this had a remainder of 0. So what we get is that our answer is x squared, 1x squared, plus 1x minus 6, and you would put the remainder 0, but we don't need to, right? 0 divided by anything, just 0. So, and now we are back to where we were before. You can multiply x plus 1 on both sides. You can factor as you go. All the steps still the same from there. However, this version, once you get very comfortable doing it, can be very, very fast. So that's really nice because you can do these problems fast. Like, what if you wanted to do division by a bunch of things? What if you don't know what divisor is going to work and you have to check a bunch of divisors? Well, that would be very helpful to us as well. Okay, let's do another one. Okay, let's do x to the 4th minus 26x squared plus 25 divided by x minus 5 again. Okay, so to set this up, this will be the coefficients to all of our x's. 1x to the 4th, we don't have an x cubed, 0x cubed. Negative 26x squared plus 0x minus 25. Again, x to the 4th, x cubed, x squared, x, and our constant. Now, the number that's going to come out here isn't negative 5. It is the 0 associated with negative 5. So the number that goes out there is positive 5. Okay, so again, down is addition, diagonal is multiplication. First number comes down, 5 times 1 is 5, 0 plus 5 is 5, right? Multiply on diagonals, but add in the columns. Okay, 5 times 5 is 25. $26 in debt, somebody gives you 25, you are now just a single dollar in debt. 5 times negative 1, negative 5. 0 plus negative 5 is negative 5. 5 times negative 5. Oh, did I make a mistake somewhere? Oh, okay, we got to backtrack a little bit. This coefficient was positive 25 to begin with. Okay, doesn't change a whole lot, but still really important. 5 times negative 5 is negative 25, but now 25 minus 25 is 0. So if this was x to the 4th, this is x cubed, x squared, x, constant, and remainder. So our answer is 1x cubed plus 5x squared minus x minus 5 plus a 0 remainder. So again, even though we're doing synthetic division, the step of putting placeholders still there. Okay, well, let's see what this looks like when it doesn't work out. We got 2 more examples and then one more quick explanation, and then we'll call it a day. Okay, we had this one before. We said this one didn't work out, so let's do it again. Okay, add going down. multiply on the diagonal. Up here comes the coefficients, 1x cubed, negative 3x squared, negative 6x, and 8, the constant. Now the number that comes out here is the 0 associated with our divisor, which in this case is 3. Bring down the first number. 3 times 1 is 3. Negative 3 plus 3 is 0. 3 times 0 is 0. Negative 6 plus 0 is negative 6. 3 times negative 6, negative 18. 8 plus negative 18, negative 10. This was x cubed. This has to be x squared, x constant, and our remainder. Okay, so our answer is x squared plus 0x minus 6 minus 10 over x minus 3. Okay, not so bad. What's one good thing too is that if you're doing what I mentioned before, that you're checking a whole bunch of factors to see what works, you only need to get up to this point. Notice that in the last two where it worked, the remainder was 0. So if you get to the point where this is 0, you found a factor of that polynomial. That's really nice. But in the event you get anything else that's besides 0, then not a factor. And it's a little bit quicker to get to that than doing long division. That part I will admit. Okay, okay, we don't need to do another full example, but I do want to show you one more thing. Let's say we want to do 2x cubed plus 4x squared plus 8x plus 16 divided by 2x plus 1. Okay, I have no idea what the number is or what the answer is. I did this completely out of the blue. Alrighty, so numbers that go in here are the coefficients. 2, 4, 8, 16. And what we're going to put out here is, again, not this 1, it is the number. It's the 0 associated with this divisor. So that 0 that is associated with it is negative 1/2. We're going to change this a little bit. Okay, maybe this fixes it. Okay, this is why we don't do things on the fly. Okay, so we changed it a little bit, but now let's go through all the steps. Bring down the 2. Negative 1/2 times 2 is negative 1. 3 minus 1 is 2. Negative 1/2 times 2 is negative 1. 13 minus 1 is 12. Negative 1/2 times 12 is 6. Oh, negative 6. Oh, and this actually works. I had no idea this was going to happen. Negative 1/2 times 12 is negative 6. 6 minus 6 is 0. Okay, so that means our answer is, this was x cubed. This must be x squared. 2x squared plus 2x plus 12. I legitimately had no idea that was going to work out. So I'm going to change the number so we didn't get some like super ugly fractions. But yeah, that wasn't supposed to happen. But now you see that in the event your divisor is linear, but not necessarily x plus something or x minus something, you have to do something like that. Okay, so with that said, that is polynomial long division. And I know this was kind of long. You see me in the flesh for the first time. This is weird. But yeah, that's that. So next up is 3.4 and 5. We're going to combine that into one section. So I will see you there. Bye.
Hi everyone, welcome back to 3.4 and 3.5. So, little break there where I was in the flesh for 3.3, but now we're back digitally. At least I can beat that. I'm not an AI allegation. So with that said, we're going to get into 3.4. However, 3.4 and 3.5 separately discuss the real and complex zeros of a polynomial function. Personally, I think it helps a little bit better with the flow if we treat it all as one big section. But, just so you know that if you're using this textbook, there are two separate sections. I think it's just easier to talk about everything all at once. So we're going to work our way up to the fundamental theorem of algebra. So if you're watching this, you might be in an algebra course, you might be in a pre-calculus course. So it's very interesting because fundamental theorem of algebra is the fundamental theorem of algebra, right? It's going to hold together a lot of the things that you talk about in your class. So with that importance in mind, let's keep it going. So let's start with the rational zeros theorem. Now, the rational zeros theorem is just this quirky little thing that's actually pretty nice from what we just did in 3.3 with polynomial long division. But what it says is this. If a polynomial has integer coefficients, which in a lot of cases it will, and p over q is a rational number, that is a zero of p of x, then p is a factor of the constant term, and q is a factor of the leading coefficient. Now, that's very wordy. Long story short, you take factors of the constant term and divide them by factors of the leading coefficient. What you get is a set of all possible rational zeros. Not a comprehensive list of all zeros, since some zeros can be irrational, like zeros you can get from the quadratic formula, but it is a list of all rational zeros that will appear in your function. So for example, if your function has a rational zero, it will appear in this list, but it just won't be a list of all of them. And you're also going to get plenty of other ones that are not zeros either. So what we're going to do is take each potential zero in our list, use synthetic division to very quickly check to see if it is a zero, and then help us factor from there. So we're not going to do that part. We're going to skip over that, right? We saw that we had to do an entire board presentation just for that. But we can take the steps for granted here. So let's start by finding all the rational zeros of 2x cubed plus 5x squared minus 4x minus 3. Okay, so how we do this is we look at the constant term and we look at the leading coefficient. The constant term is negative 3. And the factors of negative 3 would be 1 and 3, and plus and minus 1, and plus and minus 3. So here are the factors of negative 3. And then the leading coefficient is 2. And likewise, its factors are plus and minus 1, plus and minus 2, right? These are not so scary, but think about something like 6. That might be 1, 2, 3, and 6. Okay, so the set of all possible real rational zeros is given by plus or minus 1, plus or minus 3, factors of the constant divided by factors of the leading coefficient. Now, just for the sake of redundancy, we can drop the plus and minuses in the bottom. And this right here, even though not the most mathematically perfect way of writing it, this would generate all of the possible real rational zeros for our function. So if we wanted to write that actual set, it's as follows: positive 1 divided by 1, negative 1 divided by 1, positive 3 divided by 1, negative 3 divided by 1, positive 1 divided by 2, negative 1 divided by 2, positive 3 divided by 2, and negative 3 divided by 2. Had we left the plus and minuses in the bottom, what you would get is just plenty of zeros that repeat. So save yourself a little bit of work and don't put any pluses and minuses in the denominator. Okay, so now we have a set of all possible rational zeros. Not all of them are going to be zeros, obviously, right? This is too many. Here's 8 possible zeros, but we're only degree 3. There's no way that all of them could work. So what you would then do is check each one using synthetic division. However, once you check each one using synthetic division, once you find a zero, you can factor that result based on that zero. So here's what I mean. If we know that x equals 1 is a zero, well, do synthetic division using x equals 1, and you would get x minus 1 times 2x squared plus 7x plus 3. Please go back and check the 3.3 presentation to see how exactly we would get that. But essentially, x equals 1 works, so our function can factor like this. Now, the really nice thing about this, too, is that this is also factorable. Okay, well, think about it this way. I mentioned in 3.3 that polynomial division can help us go from something that can't be factored using regular methods to something that can be factored using after using long division. For example, try factoring this using anything we've talked about in the past, and you can't. But polynomial long division brought us to a point where it is factorable, right? These factors are very nice and pretty, but we needed long division to do that. So it is a tool to factor. Okay, just to summarize 3.3. But now, if we want to find all the rational zeros, well, now just set all of these equal to 0, and we would get x equals 1, x equals -3, and x equals -1/2. Degree 3, 3 zeros, nothing missing, and here's one more interesting part about rational zeros theorem. All 3 of these zeros did appear in that list that we just had. So we got 5 other zeros that were not true, but all the zeros that are here, all these rational zeros, did appear in that list. We just happened to use x equals 1 as our starting point to do long division. But you could have done the exact same thing with x plus 3. You could have done the same thing with 2x plus 1. So rational zeros theorem says we have a way of getting all the possible rational zeros. Well, you might find this is a little inefficient for an example like this one. Your constant term is 8. So the factors of 8 are 1, 2, 4, and 8. And then your leading coefficient is 3, whose factors are 1 and 3. So the set of all possible real rational zeros would be plus and minus 1, plus and minus 2, plus and minus 4, plus and minus 8 over 1, 3. Again, take the constant factors, divide them by the leading coefficient factors. And now the set of all these zeros is a lot longer. So this is not fun. So the point here is that the rational zeros theorem only gives us a set of possible zeros, not a very necessarily useful set. So you would have to go through and check all of these. So part of the reason why rational zeros theorem isn't super useful is that you could be spending a lot of time to find a rational zero that might not actually even be a zero, right? This is a set of possible rational zeros. What if your function doesn't have any rational zeros to begin with? So we'll take for granted that we will check each using synthetic division. And again, once we find a zero, factor that result. So let's just say that we knew that 2/3 was a zero. Well, knowing that 2/3 is a zero, then we would get something like this. We could factor this by taking out a 3. And then to find the remaining zeros, well, we would need to do quadratic formula on that. So in total, all of our zeros of our function would be 2/3, and after doing quadratic formula, 1 plus and minus square root of 5. So, it would have taken you a long time just to get to 2/3. But again, the point here is that we went from something that you could not find the zeros for to something that we could find the zeros for, even if not that pretty. So that's just a lead in to the point that we actually want to look at, and that's the fundamental theorem of algebra. Okay, if your polynomial is degree n, it has at most n real zeros. We looked at that in 3.2. In 3.2, we said, we would have a degree 3 polynomial, but we would only have like 2 zeros. So like what happened? Multiplicity describes some of that, but what we're going to do here in 3.4 and 5 is perfectly describe that. Okay, but also don't forget that all real numbers are also complex numbers. Oh, it's been a long time since we've talked about complex numbers, just numbers that may contain I. So what happens if you have a degree 10 polynomial that has only 4 real zeros? Where are the other 6? Well, we saw in the last, in 3.2, that you could have multiplicity describe some of it, but not always all the time perfectly describe it. So that brings us to the fundamental theorem of algebra. Every polynomial function like this of degree n greater than or equal to 1 has at least one complex zero. So don't forget, real numbers are also complex numbers. So just because it has at least one complex zero doesn't necessarily mean it has an imaginary zero, right? Real numbers, 2, 5, -3 halves. those are all real numbers. Fundamental theorem of algebra says we have at least one complex zero. But the main result of fundamental theorem of algebra isn't necessarily that part. It is factorization theorem. Factorization theorem says that all polynomials of degree at least 1 can be factored as this. P of x equals a sub n, x minus c1 times x minus c2, all the way to times x minus cn. A sub n is the leading coefficient, and ci are just non-distinct complex zero factors of p of x. Okay, that's really, really interesting. Every polynomial can be factored. Maybe the factors necessarily aren't super pretty, but it can be factored. So going back to this, we say those zeros are non-distinct because, for example, you can have a degree 7 polynomial that looks like this. And we actually described this in 3.2, where we had the possibility that like only 3 zeros for a degree 4 polynomial, but the multiplicities of those 3 add to 4. So that's kind of what's happening here. Point is, those zeros, those factors, don't need to be distinct. Okay. Then, if every polynomial has at most n real zeros and at least one complex zero, then every polynomial of degree n has exactly n complex zeros. Well, that is, if you include multiplicity, if you include irrational zeros like you could get from quadratic formula, if you include imaginary zeros, every polynomial has exactly n complex zeros. So before we had a degree 10 polynomial and we said it only had 4 real zeros. Where are the other 6? Well, they're imaginary. Okay, degree 5 polynomial with only 3 real zeros has 2 more complex zeros. A degree 12 polynomial with only 8 real zeros has 4 more complex zeros. And I'm not going to gush like crazy. Normally, when I'm talking about this in person, I get very animated. That's just what the in-person lectures look like. But I get really animated to the point that I'm like, this is really, really important. It holds the study of algebra together. How do you have the fundamental theorem of algebra, or how do you not have the fundamental theorem of algebra and be able to do anything that we've done in this course together? So whether or not you're watching my videos because you're in one of my 16-week classes, whether or not you're watching my video because you're in my 3-week classes, whether or not you're watching my video because you're in some other class, everything you've learned in algebra and almost all of mathematics can't be held together without the fundamental theorem of algebra. So that's my little bit of online gushing. So that brings us to 2 more theorems that we need before we actually start to apply these things. Conjugate pairs theorem says this. If you have a polynomial that has x equals a plus b squared of c, that's an irrational zero of the polynomial, then x equals a minus b squared of c is also a zero. That is, all irrational zeros come in conjugate pairs. A plus b squared of c is a zero, then a minus b squared of c is a zero. Well, if x equals square root of 5 is a zero, then x equals negative square root of 5 is a zero. If x equals 11 plus square root of 20 is a zero, then x equals 11 minus square root of 20 is a zero. If x equals negative 8 minus square root of 13, then x equals negative 8 plus square root of 13 is a zero. If x equals 2 plus 2 square root of 2 is a zero with multiplicity 5, then x equals 2 minus 2 square root of 2 is a zero, also with multiplicity 5. And this is a perfect example as to why quadratic formula always gives 2 zeros when your discriminant doesn't equal 0. For example, in that second example we did for rational zeros theorem, the 2 other zeros to the function were 1 plus square root of 5 and 1 minus square root of 5 via quadratic formula. So this is why quadratic formula always gives a pair of zeros, not only when it's irrational, but also when it's rational and real. Okay, well, we also have another conjugate pairs theorem that's very similar. If you have an imaginary zero, a plus bi, then x equals a minus bi is also This should say complex. That's a mistake. If a plus bi is a complex zero, then a minus bi is also a complex zero. That's my bad. So if x equals positive I is a zero, then x equals negative I is a zero. If x equals 11 plus 20i is a zero, then x equals 11 minus 20i is a zero. If x equals negative 8 minus 13i is a zero, then x equals negative 8 plus 13i is a zero. If x equals 2 plus 2i is a zero with multiplicity 5, then x equals 2 minus 2i is also a zero with multiplicity 5. So when quadratic formula has two imaginary answers, it's always why there's two imaginary answers when the discriminant is less than zero. So all of this kind of coming back to 1.3 when we initially learned quadratic formula. Okay, so let's just practice finding some missing zeros, but what we eventually want to do is construct polynomials, which is a lot more interesting. Okay, so let's say our polynomial is degree 5, and its zeros are 6, negative 4 plus 3i, and 2 minus square root of 7. I gave you 3 zeros, but we're degree 5. We are missing 2 zeros. Well, negative 4 plus 3i is a 0, so negative 4 minus 3i is also a 0. 2 minus square root of 7 is a 0, so 2 plus square root of 7 is also a 0. So in total, I gave you 3. We found 2 more, all 5 zeros right there for us. Okay, let's say we have a degree 10 polynomial and it has zeros negative 10, 0, negative 1 minus 2i, 2 minus 3i, square root of 15, and 1 plus 5 square root of 2. I gave you 1, 2, 3, 4, 5, and 6. Well, degree 10, I give you 6 zeros. We're missing 4 zeros. Because negative 1 minus 2i is a 0, negative 1 plus 2i is a 0. Because 2 minus 3i is a 0, 2 plus 3i is a 0. Because positive square root of 15 is a 0, negative square root of 15 is a 0. Because 1 plus 5 square root of 2 is a 0, 1 minus 5 square root of 2 is also a 0. And then we had 6 zeros to start. We found 4 more, all 10 zeros right there. Okay. Well, let's do, I think, one more example of this. Degree 17. The zeros are 2 multiplicity 3, 4 plus 5i multiplicity 2, 3 minus square root of 10 multiplicity 5, and let's find the remaining zeros. Well, I gave you 3 plus 2 is 5, 5 plus 5 is 10, so including multiplicities, 10 zeros, but we're degree 17, so we're missing 7. 4 plus 5i is a 0 with multiplicity 2, so 4 minus 5i is a 0 with multiplicity also 2. 3 minus square root of 10 is a 0 with multiplicity 5, so then x equals 3 plus square root of 10 is also a 0 with multiplicity 5. So then we had 10 zeros to start, and we found 2 and 5 more, including multiplicities. How lovely, how nice. Okay, well, that brings us to constructing polynomials, and this definitely the wrap up to the course. Unfortunately, it doesn't end on such a beautiful storybook note. We have one more section at the end, but this is really, really the key to algebra, to any algebra class. So find a polynomial of degree 3 that has leading coefficient 1 and these zeros. Well, this comes back to factorization theorem. What we're normally used to doing is starting with a polynomial and then finding the zeros. But what we can now do is construct polynomials given zeros. So the information that we're given is that our polynomial is degree 3, our leading coefficient, and we have 3 zeros. So what we're going to use is factorization theorem. Now, specifically, since we're degree 3, we're only going to go up to x minus c1, x minus c2, x minus c3. And now, let's just plug in the information that we have. The leading coefficient is 1. Our first 0 is negative 2. Our second 0 is 3. And our third 0 is 7. So leading coefficient 1 First 0 is -2, second 0 is 3, third 0 is 7, and we can simplify x minus -2 to x plus 2. We also don't need this 1 out in front. So this would be the perfectly factored version of a polynomial that fits this criteria. However, we know how to FOIL. We've practiced FOILing in the past, and we would get this, right? So chapter P stuff to FOIL, I don't want to go over that here. If you need help, by all means, go back to that, or just use an online calculator. I didn't say that out loud. Okay, anyway, so we have the polynomial that fits this criteria. Okay, degree 2, leading coefficient -1, and zeros -4 and 0. Okay, so factorization theorem says this, but since we're degree 2, we're only going to go up to x minus c2. Well, our leading coefficient is -1, our first 0 is -4, and our second 0 is 0. All right, well, x minus -4, x plus 4, x minus 0 is just x, and if we ever have just plain x's, we like to write them in front. So we get -x, x plus 4, and you can distribute -x to get the polynomial that does this. So all it is, plugging and chugging, and then in some cases a lot of FOILing, but we don't need to do the FOILing here. Okay. Degree 4, leading coefficient 1 with zeros 0, 2, 5, and 10. Okay, well, if we're degree 4, we're going up to x minus c4. Our leading coefficient is 1. Our first 0 is 0. Second 0 is 2. Third 0 is 5. Fourth 0 is 10. All right, well, x minus 0 is just x. And this nice factored version, but we can practice our FOILing. So these are the really the best examples to a fundamental theorem of algebra, just using the results of the factorization theorem. Okay, leading coefficient 3, degree 4, with zeros -5, -1, 2, and 6. All right, well, degree 4, go up to C4. Leading coefficient is 3. Our first 0 is -5. Second 0 is -1. Third 0 is 2. Fourth 0 is 6. We can simplify x minus -5 and x minus -1. And, now that we've done a couple examples, I just want to throw out there that this is usually a pretty nice form. If you can get to this point, you really learned the course. And as you see the next couple examples, it's only going to get worse when it comes to FOILing, right? Foiling out 4 things is no fun by any stretch of the imagination. So again, the stuff to take away here is really getting up to this point where, we have a polynomial that equals this thing. But the point is that even if you don't know how it factors, it does factor one way or another. Okay, let's start to introduce some imaginary zeros, right? We said some weird stuff about irrational zeros, about imaginary zeros, so let's put that into here. Okay, well, polynomial is degree 4. Our leading coefficient is 2. Our first 0 is -1, then 3, then I, then -I. Okay, let's simplify our negative negatives, and we get a perfectly factored polynomial. So this is what it is when you expand it, right? Practice your FOILing. This would be a 1.4 practice. P3, FOILing regular polynomials. But in 1.4, we practice doing that with I. So go back to 1.4 if you need help with that. But point is that this can be factored if we allow our zeros to be i's. And zeros are i's, and even though we never wrote stuff like this in the past, it doesn't change the fact that this is, say, a factor of our polynomial. So something to keep in mind. All right, degree 3, leading coefficient 1, 2, 1 plus 3i, 1 minus 3i. Degree 3, leading coefficient is 1. First 0 is 2. Second 0 is 1 plus 3i. Third 0 is 1 minus 3i. So a little uglier now, but here make sure you distribute a negative sign to both, and make sure you distribute a negative sign to both. This nice factored version, and you already start to see how crazy this could get. So yeah, be careful about that. But again, it's all really just plugging and chugging. But what we can now introduce is that you don't necessarily need to be given all the zeros to solve these types of questions. So degree 3, but I'm telling you only 2 of the zeros. Specifically, I am telling you only 2 of the zeros. So degree 3, leading coefficient is 1. First zero is -1. Second zero is 2 plus 2i. But notice that we have a factor that we haven't filled in yet. Well, don't forget that if 2 plus 2i is a 0, then 2 minus 2i is also a 0. So I can omit information, and you could still find that information the exact same way. Okay? So minus minus, distributing negative signs we get here. And yeah, maybe this answer doesn't look so bad, but when you go to FOIL something out like this that's got 3 parts each, it's not pretty. So definitely practice doing that. Okay. Degree 4, leading coefficient 1 with zeros 0, 4, and 1 minus I. Again, degree 4, but I only give you 3 zeros. Okay, well, here's degree 4. Leading coefficient is 1. First 0 is 0. Second 0 is 4. Third 0 is 1 minus I. But don't forget that if 1 minus I is a 0, then 1 plus I is a 0. So the first few examples, I gave you both parts in the pair, but I don't always have to do that. Here, I can just give you 1 minus I, and you find the other one. However, I could also just give you both in the pair. So I can go both ways. Let's distribute negative signs here. X minus 0 is x. 1 times x is just x. This is a nice, pretty answer. And there it is after you FOIL. Okay. Degree 3, leading coefficient 4 with zeros 1 and 2i. So degree 3, leading coefficient is 4. First 0 is 1. Second 0 is 2i. And then our missing 0 is negative 2i. Okay, and there we go. Degree 3, leading coefficient -2. 0 is -1, negative 3i. Well, degree 3, leading coefficient is -2. First 0 is -1. Second 0 is negative 3i. But if negative 3i is a 0, then positive 3i is also a 0. Distribute some negative signs, and then FOIL. Lots of foiling. I know I'm skipping through all of that, but I think by now, if we're talking about factorization theorem and fundamental theorem of algebra, that the foiling part is very much deep-rooted into our minds. Okay, degree 3. Well, let's start to introduce some irrational zeros like square root of 7. All right, well, they function almost exactly like i's. If anything, they're a little bit nicer to evaluate when you are foiling. Okay, degree 3, leading coefficient is 1. First 0 is 3. Second 0 is square root of 7. Third 0 is negative square root of 7. Distribute that negative, and now we get here. Okay. Well, we can very quickly change this to me only giving you one of the irrational zeros. So degree 3, leading coefficient 1, 0 is 2, and square root of 3. I only gave you 2 of them. You can find the third one. Degree 3, leading coefficient is 1. First 0 is 2. Second 0 is square root of 3. But if positive square root of 3 is a 0, then negative square root of 3 is a 0. And then we are rinsing and repeating. Okay. Polynomial of degree 5 with leading coefficient 1 with zeros 2 and -5, each with respective multiplicities of 3 and 2. So here's how we could set this up. If we're degree 5, we got to have 5 factors. Our leading coefficient is 1. Our first 0 is 2, but we have 2 3 times. Then our next 0 is -5, but -5 multiplicity 2. Well, we can simplify this right away to be x minus 2 cubed and x plus 5 squared. So when you're going to set this up, if you were to show me work, right, if we're doing like physical assignments, you wouldn't need to show me doing this step if you can jump right to here, right? Given just this information, you probably could have jumped to what the answer was going backwards. But my point is if you are comfortable jumping right to, an exponent version of the factored form, that's totally fine too. I wouldn't have a freak out about that. But then, yeah, maybe now things will start to look a little ugly in our functions. But again, multiplicity, not changing a whole lot, just adding some exponents. Okay, degree 10, leading coefficient 1, x with zeros, x equals 0, multiplicity 2, x equals 1, multiplicity 5, x equals -6. No multiplicity said, so we assume it's multiplicity 1, and x equals 2, multiplicity 2. So here's a great example as to why we wouldn't write out all 10 zeros. For x equals 0, multiplicity 2, we'll do x minus 0 squared. For x equals 1, multiplicity 5, x minus 1 to the 5th. For x equals -6, just x minus -6. And x equals 2, multiplicity 2, x minus 2 squared. You would be very welcome to write out all 10 zeros if that helps you, but I think you'll find it's very tedious to be writing out something that long when you could just be using exponents. Here's a nice simplified version, and yeah, either practice foiling or enlist the help of an online resource. Okay. Degree 7, leading coefficient -5 with the following zeros: -2, 1 multiplicity 2, and 1 plus I multiplicity 2. All right, so we are degree 7. Our leading coefficient is -5. Our first 0 is -2. Our second 0 is 1 multiplicity 2. Our next 0 is 1 plus I multiplicity 2. But don't forget that if 1 plus I is a 0, then 1 minus I is a 0 with the same multiplicity, right? I gave you 1, 2, 3, 4, 5 zeros to start, but we were degree 7, so we knew that we were missing 2 zeros. And that came in the form of just one more factor with a squared. All right, distribute some negatives, simplify that. And yeah, these are getting even better by the slide. All right. Degree 7, leading coefficient 17 with zeros: -5 multiplicity 2, 0 multiplicity 3, 5 multiplicity 2, and 23i. All right, degree 7, we have leading coefficient is 7. We have x equals -5 multiplicity 2, so we'll throw a squared there. X equals 0 multiplicity 3, so x minus 0 cubed. X equals 5 multiplicity 2. Then we get x minus 23i, but don't forget that if positive 23i is a 0, then negative 23i is also a 0. Simplify a little bit, and yeah, you all definitely knew 5,620,625, right? No problem at all. Okay, degree 10, leading coefficient 1, x equals 1 plus I multiplicity 2, and square root of 3 multiplicity 3. I gave you 2 zeros plus 3 zeros for a total of 5. So if we're degree 10, we're missing 5 zeros. Okay, well, we have 1 plus I multiplicity 2. So this is x minus 1 plus I squared. But if 1 plus I is a 0, then 1 minus I is a 0 with the same multiplicity. Well, we have x minus square root of 3, multiplicity 3, so cubed. If x equals square root of 3 is a 0, then x equals negative square root of 3 is also a 0. Okay, simplifying some negative signs, and we get this monstrosity that I would never expect somebody to actually do in person. But there we go. All righty, we're nearing the end, but we continue. All right, leading coefficient negative 57 with zeros 3 plus 7i, multiplicity 3, negative 4 plus 6i, multiplicity 3. So we would have negative 57 leading coefficient. Our first zero is 3 plus 7i 3 times. Well, if 3 plus 7i is a 0, then 3 minus 7i is a 0 3 times. If negative 4 plus 6i is a 0 3 times, then negative 4 minus 6i is a 0 3 times. Okay, this is fun. This polynomial, I think I tried plugging this into an online resource, and it just wouldn't give me an answer back. It said it was too big. So, as we get a little crazier, I would never expect you to fully expand it, but especially getting up to this point is definitely the key new part to this section. And that brings us to the end of 3.4, 3.5. So normally that would be a really nice storybook to end with, like, this is the fundamental theorem of algebra, but we have one more section that is still in a, not necessarily in the progression of quadratics to polynomials to real and complex zeros, but rational functions still important enough for us to talk about. So we'll do that in 3.6 for the final section of this algebra course and these algebra videos that you have been watching. So until then, I will see you in 3.6. Bye. Hi, everyone. Welcome back to the final section of this algebra course, the final section of this chapter. We're going to wrap up the course by talking about rational functions. So normally you would think that talking about like real and complex zeros of a function is like the perfect way to end an algebra course. But we got to tack on one more section since it's the end of chapter 3. So yeah, we'll get right into it. Some similar stuff, some new stuff, but nothing here that's really going to blow anybody's mind, I don't think. So rational numbers are numbers of the form p over q, where q doesn't equal 0. So rational functions are functions of the form p of x over q of x, where q of x does not equal 0. P of x and q of x are themselves polynomials. So as a reminder, no radicals, no absolute values, no rational exponents, right? Just straight x's to whole number powers. The domain of rational functions are all the places where the denominator does not equal 0. But you know what? We talked about that in 2.4 plenty of times. But just as a reminder, 1 over x minus 3, we want to make sure the denominator does not equal 0. So in this case, add 3 to both sides. So x can be anything to the left of 3, everything to the right of 3, just not 3 itself. The domain of x plus 1 over 4x minus 8. So denominator can't equal 0. Add 8 to both sides, divide by 4, and x can be everything to the left of 2 with everything to the right of 2. Okay, then here we go. X minus 1, denominator still can't equal 0. So add 1 to both sides. X can be anything to the left of 1 with everything to the right of 1. If you want to spend a little bit more time finding domains, I recommend checking out the video on 2.4. Okay, here, x minus 2, not allowed to be 0. X can't be 2. So x can be anything to the left of 2 with everything to the right of 2. All right, here we have two things. So x can't be negative 2 and it can't be 3. Set each one not equal to 0. So we can be everything to the left of negative 2, everything between negative 2 and 3, and everything to the right of 3. Okay, x squared minus 6x plus 8 can't be 0, right? Just keep taking the denominator not equal to 0. Factor, set each factor not equal to 0. We can be everything to the left of 2, everything between 2 and 4, everything from 4 to infinity. Okay, well, same thing here. Set the denominator not equal to 0. Factor, set each factor equal to 0. We can be everything to the left of one of them, everything between them, everything to the right of them. And that's it's going to be what happens for most of the time when it comes to two factors. If you have three factors, it works the same way. You would have left of the leftmost one, between them, and everything to the right of them. Oh, speaking of, let's do that right here. So we don't care about multiplicities here. We just care about what the zeros are. So x can't be 6, negative 54, positive 1/2 right here. Add 1 to both sides, divide by 2. So in order, we can be everything to the left of negative 54, everything between negative 54 and 1/2, everything between 1/2 and 6, and everything from 6 to infinity. So just be careful to write domain in order of how you would read x values from left to right. Okay, so basics domain, we've talked about that. But domain actually has an influence on this new thing called a vertical asymptote. So asymptotes in general are vertical or horizontal lines that your graph never crosses. So for example, in this rational function, we have 2 lines that are creating this weird behavior where we get really, really close to it, but we'll never hit it, get really, really close to it, but never hit it. And same thing for the part up here. Now the question is, when do they occur, and how do we know what the behavior is to each one? So some of the functions we were looking at before, x plus 1 over 4x minus 8, well, we weren't allowed to be equal to 2, so 2 was a vertical asymptote. X squared plus 2 over x plus 2x minus 3, x wasn't allowed to be equal to negative 2 or 3, so we get 2 asymptotes. Now, we might notice that there's slightly different behavior here, but that's just going to be the nature of rational functions, and we'll talk about that. So if you're finding the domain of a rational function, no matter what, always set the original denominator equal to 0. Domain of a function will never change. No matter how you can simplify, no matter what you can do to a function, there was one of the functions that we were just doing domains for that you could have simplified first. However, domain is always the original denominator, no matter what, period. However, to find vertical asymptotes, to find these vertical locations where things are weird, start by simplifying the function. After you do that, then you set the new denominator equal to 0. So you have some original function, no matter what it looks like. Don't try and cancel anything out. To find its domain, simply set the denominator equal to 0. But when we're going to look for vertical asymptotes, start by simplifying. So you already found the domain, now you simplify. Okay, so after you simplify, set the new denominator equal to 0. And now those locations that you get for x will result in vertical asymptotes, specifically vertical lines of the form x equals h. Now, what you might be wondering is, what about all the places that did cancel out? Well, right, setting the new denominator equal to 0 means that whatever corresponding values we get came from factors that didn't cancel out. Well, if a factor does cancel out, it results in what we call a whole. Now, here's the key part. Even though that factor canceled out, it still doesn't change that original domain that we found with the original denominator. We can't ignore where our simplified function came from. So we can simplify it. It could be easier to graph after we simplify, but we can't magically start plugging in values that we don't have. However, to graph a whole, all we need to do is plug in that x value that we canceled out. But we'll talk about that. So to graph rational functions, graph a simplified version of that graph. So for wholes, what we're going to do is draw an open circle or a break in the graph. But then the question becomes is, how do we know which infinity each side of an asymptote it goes to? So we see that we're going to graph a simplified version. We see that we're going to graph wholes when they're applicable, but that doesn't tell us anything about the asymptotes, right? The asymptotes themselves, it's just going to be a vertical line that we can put like a dotted line for. But when it goes to actually graphing it, how do we take into account that weird behavior to each side? So for asymptotes, we determine which infinity each side goes to by plugging in numbers really, really close to each side. So let's do the example 1 over x minus 3. Well, this is fully simplified, nothing else we need to do. And when we set this new denominator equal to 0, we get a vertical asymptote at x equals 3. So to take care of a vertical asymptote at x equals 3, we need to figure out what's the behavior as we get closer to 3 from the left. Are we going up as we approach 3 or down as we approach 3? And likewise, when we approach 3 from the right, are we going up or are we going down? So what we're going to do is plug in numbers really, really, really close to 3. So for example, you would plug in something like 2.999 for the left and 3.001 for the right. Now, here's something to keep in mind. We don't actually care what the value is when we plug these numbers in. We already know that the behavior is either going to infinity or negative infinity from each side. So all we care to figure out is the sign of infinity. So for example, when we plug in 2.999, well, 1 over 2.999 minus 3 is 1 over negative 0.001, and this is a positive number divided by a negative number. Positive divided by a negative is a negative number. So in this case, to the left of x equals 3, we are approaching negative infinity. Again, did not care at all what the value was. All we care about is the sign of infinity. For 3.001, okay, well, 3.001 minus 3 is positive 0.001, and this is a positive number, so 1 divided by a positive number will be positive infinity. So from the left of 3, we're going to go down to negative infinity, but from the right of 3, we're going to go up to positive infinity. So there we go. As we approach 3 from the left, as we approach 3 from the right, negative and positive respectively, just like we found. Now, this weird behavior that's happening down here, we'll come back to that. Okay, let's do the same thing, but for 1 over x minus 1. Well, we have a vertical asymptote at where this denominator is equal to 0 at x equals 1. So we're going to plug in numbers very, very close to 1 from the left and from the right. So let's plug in 0.999 for the left and 1.001 for the right. When we plug in 0.999, we get 1 over negative 0.001, which is negative. So 1 divided by a negative number is a negative. 1.001, well, 1.001 minus 1 is 0.001, which is positive. 1 divided by a positive number is a positive infinity. So we're going to graph a vertical asymptote at x equals 1. Left side is going to go down, right side is going to go up. Okay. Let's do this again, but now we have two things, right? X squared minus 9 is x plus 3x minus 3. So we're going to do a vertical asymptote at negative 3 and at 3. We have two vertical asymptotes, and that's totally okay. So, however, because we have two vertical asymptotes, we need to check the behavior from each side for both of them. So let's start with x equals negative 3. For the left, we're going to plug in negative 3.001. And for the right, we're going to plug in negative 2.999. So just be very careful, right? Negative, normally we would associate the 0.999 from the left when it comes to positive, but when we're negative, negative 3.001 is to the left of negative 3. Okay, so let's plug it into this factored version. Negative 3.001 plus 3, negative 3.001 minus 3. And I again want to remind you, we don't care about the value, we only care about the signs. So forget about trying to calculate this thing. Here, negative 3.001 plus 3 is just negative, and negative 3.001 minus 3 is also negative. So 1 divided by a negative times a negative, well, negative times a negative is a positive. So in total, positive infinity. Okay. Let's do the same thing for negative 2.999 plus, or negative 2.999 from the right. So this will be positive. This will be negative. Positive times a negative is a negative. So in total, we get negative infinity. So for this specific vertical asymptote, x equals -3, we're going to go up from the left and down from the right. Okay, well, we got to repeat the same process for the second vertical asymptote. So let's do 2.999 for the left and 3.001 for the right. 2.999. All right. This one, positive. This one, negative. Positive times a negative is a negative. Whole thing, negative infinity. 3.001. Okay. This is positive. This is positive. Positive times a positive is a positive. So in total, we get positive infinity. So for this vertical asymptote, we're going down and then up from each side. So in total, we went to positive infinity, negative infinity, negative infinity, positive infinity. So positive, negative, negative, and positive. Who chose the specific window so that's so hard to tell? I don't know. It might be somebody on the screen's fault, but I think we get the idea. Okay, well, let's graph with some holes now. So holes occur at the locations where factors cancel out. So let's start by simplifying. So simplify first. If a factor does not cancel out, it's a vertical asymptote. But if a factor does cancel out, it is a hole. All right, so x squared minus 9 is x plus 3x minus 3. And we can cancel out x minus 3. Okay, so what we're going to do is graph simplified version of the graph. This is the simplified version, but we're going to draw a hole where this factor canceled out. So this corresponding x value is x equals 3. And since there's no more denominator, it's actually pretty nice. So there's no more vertical asymptotes. So in total, we're just going to graph x plus 3 and put a hole at x equals 3. And that's the extent of drawing some rational functions, right? We're still very low, but nonetheless, this is how this works. Okay, let's do the same thing, but flipped and see how this would work. Well, we're going to simplify first. And same thing, if a factor doesn't cancel out, vertical asymptote. If a factor does cancel out, hole. Okay, well, x plus 3x minus 3 and x minus 3 cancels out. So we're going to graph this simplified version, but x equals 3 once again canceled out, right? I know x minus 3, the factor canceled out, but the corresponding x value to x minus 3 is x equals positive 3. So there's a vertical asymptote at this location that did not cancel out, and x equals -3. From the left of -3, the graph goes down. From the right of -3, the graph goes up. You could check this doing that 2.999 and 3.001 stuff we did before, but here we go. Negative and positive, and there is our hole for this function. Okay, let's do another one. X plus 2 over x squared minus 2x minus 8. So let's simplify first. If a factor if a factor doesn't cancel out, it's a vertical asymptote. If a factor does cancel out, it's a hole. So x squared minus 2x minus 8, x minus 4 times x plus 2. X plus 2 cancels out. So we're going to graph 1 over x minus. This should be 1 over x minus 4. I don't know how that happens. So we're going to graph 1 over x minus 4, like it's right here, but we're going to graph a hole at x equals -2. So there's a vertical asymptote at x equals positive 4, right? Again, this should be minus. So when you go to x equals 4 from the left, you go to negative infinity. When you go to x equals 4 from the right, you go to positive infinity. And there we go. All right, some more graphs with holes. Here we go, 3 minus x over x squared minus 6x plus 9. All right, let's simplify first. Okay, denominator factors to x minus 3 squared, and this is pretty close. So what if we factored out a -1 from the top? Okay, well, x minus 3, well, one of them cancels out. So we're going to graph this simplified version. However, there's a vertical asymptote at the location that did not cancel out. So there's a vertical asymptote at x equals 3. So from the left of 3, we go to positive infinity, a little backwards from before since we have this negative sign up here. And from the right of 3, we're going to go to negative infinity. Now you might be wondering, why isn't x equals 3 a whole, right? X minus 3 canceled out. Well, it didn't perfectly cancel out. It didn't cancel it out everywhere. It's still remaining in the denominator. So its status as a vertical asymptote has to supersede that of a whole, right? You can't have a vertical asymptote in a whole. That doesn't make any sense. So in this case, its graph would look identical to negative 1 over, was it x plus 3? No, negative 1 over x minus 3. Okay. Well, that's vertical asymptotes. That's wholes a little bit. So now let's talk about horizontal asymptotes. Now you're probably thinking, oh my God, we keep getting closer and closer to the end, and the stuff keeps getting harder and harder. Don't worry, it's actually not that bad. If anything, it's even better. So vertical asymptotes are vertical lines that your graph never crosses. But horizontal asymptotes are kind of funny. Horizontal asymptotes are horizontal lines that your graph sometimes can cross. So we can't necessarily explain it right now. Horizontal asymptotes essentially are tied to the end behavior of rational functions. We talked about end behavior for polynomials, but we can't really talk about end behavior for rational functions. It's a little quirkier than that. And if anything, it actually requires Calculus 1 to come up with, including all of these below rules to help us find horizontal asymptotes. So what we're going to do is compare the degrees of the numerator and denominator, right? Rational function, numerator and denominator. Compare the degree of the numerator with the degree of the denominator. In this case, when the degree of the numerator is less than the degree of the denominator. So for example, something like x squared divided by x cubed, well, you would have a horizontal asymptote at y equals 0, or also just the x-axis. If the degrees are equal, then there's a horizontal asymptote at the quotient of the leading terms. Okay, that one's kind of weird. We'll come back to that one. However, if the degree of the numerator is bigger, there is no horizontal asymptote. So it's either going to be y equals 0 at the quotient of leading terms or no horizontal asymptote. Okay, so let's just do 2 slides entirely finding horizontal asymptotes. Okay, in this case, the numerator is 1, denominator is x minus 3. The degree of the denominator is 1 for x to the 1. Well, since there's no x in the numerator, this is degree 0. So numerator is 0, denominator is degree 1. So the degree of the numerator is less than the degree of the denominator. And now just pull the rule from the last slide. When the numerator is less than the denominator in terms of degrees, there is a horizontal asymptote at y equals 0. Okay. Here we have 3x squared minus 1 over x plus 2. The degree of the numerator is 2. Degree of the denominator is 1, right? X to the 1. Well, in this case, the degree of the numerator is bigger than the degree of the denominator, 2 over 1. Okay, when the degree of the numerator is bigger, there is no horizontal asymptote. Okay. Find the horizontal asymptote of x plus 1 over 4x minus 8. Okay, well here, x is degree 1, 4x is also degree 1, so the numerator and denominator are both degree 1. They're both equal. So here's what we're going to do. We're going to take those leading terms and divide them. So there would be a horizontal asymptote at y equals x over 4x. Well, cancel out an x and we get 1/4. So there is a horizontal asymptote at y equals 1/4. All right, horizontal asymptote of 2x over x squared plus 1. Degree of the numerator is 1 for 2x to the 1. Degree of the denominator is x squared, degree 2. So the numerator is 1, denominator is 2. The degree of the numerator is less than the degree of the denominator. So we have a horizontal asymptote at y equals 0, right? We're just pulling rules from the last slide. Here, 3x cubed plus 2x squared plus x over 2x plus 5. The degree of the numerator is 3. Degree of the denominator is 1. Numerator is bigger. The rule for bigger numerator is no horizontal asymptote. Okay, so let's do another slide of these. Horizontal asymptote of 5x plus 2 over negative 3x plus 1. Degree of the numerator is 1. Degree of the denominator is also 1. So we're going to take those leading terms and divide them. Cancel out the x, and we get negative 5/3. Okay, horizontal asymptote of x cubed plus 1 over 4x to the 4th plus 1. The degree of the numerator is 3. Degree of the denominator is 4. So degree of the numerator is less than the degree of the denominator. So in the case where it is less than, there's a horizontal asymptote at y equals 0. All right, x squared plus 2 over x plus 2x minus 3. Well, let's FOIL out the denominator. And now you see degree 2 in the numerator, degree 2 in the denominator. So take those leading terms and divide them. X squared divided by x squared is just 1. 4x to the 4th plus 1 over x cubed plus 1. Degree of the numerator is 4. Degree of the denominator is 3. So numerator is bigger. There is no horizontal asymptote. All right, one more example. Here, the degree of the numerator is 2. Degree of the denominator also 2. So take those degree 2 terms and divide them, and we get negative 3/4. So horizontal asymptotes, even easier to find. Okay, and now let's put all of this together to graph rational functions. This is how we're going to sunset algebra in chapter 3. So here we go. So to graph a rational function, start by finding the domain. You don't necessarily need it to graph. However, it is a very important part of the function, and it helps remind us that we can't magically start plugging in values. It reminds us that we need vertical asymptotes and we need holes. So set the original denominator equal to 0. Then simplify the function. If a factor cancels out, it's a hole. But if a factor doesn't cancel out, it's a vertical asymptote. And then check numbers to the left and right of that vertical asymptote to determine which side, to determine which infinity each side goes to. And we like to sketch vertical asymptotes as dotted lines. To find horizontal asymptote, we're going to sketch that as a dotted line, but just use the 3 rules that we just talked about. Okay, find zeros and x-intercepts, set the numerator equal to 0, and last but not least, find the y-intercept by setting x equal to 0, right? Come full circle to x and y-intercepts that we've been doing since very early in chapter 2. And we sketch based on all of this information. Okay, let's graph 1 over x plus 5. So domain, we want to make sure that the denominator doesn't equal 0. Subtract 5 on both sides, so we can be everything except negative 5, which is everything to the left of negative 5 with everything to the right of negative 5. Okay, simplify the function. Well, in this case, there's nothing to simplify. So that means we have a vertical asymptote at the factor that didn't cancel out, which is x equals negative 5. So to the left of negative 5, we're going to go to negative infinity. To the right of negative 5, we're going to go to positive infinity. And there's no holes since we didn't have any factors to cancel out. Horizontal asymptote, let's compare the degree of the numerator and degree of the denominator. Degree of the numerator is x to the 0, so just 0. Degree of the denominator is 1, x to the 1. So the numerator is less than the denominator in terms of degree. When the numerator is less than, there's a horizontal asymptote at y equals 0. X-intercepts, we set the numerator equal to 0. However, obviously 1 is never going to equal 0, so there's no x-intercepts. That's totally fine. Y-intercept, we're going to set x equal to 0. So 1 over 0 plus 5, 1/5. Okay, all that said together, all that put together, all that said and done, right? We've come a long way. There we go. Alrighty. Another one, 6 over x squared minus 1. Let's start with the domain. Need to make sure the denominator doesn't equal 0. Well, x squared minus 1 is x plus 1, x minus 1. Set each one equal to 0. And we get everything to the left of -1 with everything to the right of -1. Sorry. And we get everything to the left of -1, everything between -1 and 1, and everything to the right of 1. Simplify the function. Well, nothing we need to do here. So that means we have vertical asymptotes at both values that did not cancel out. To the left of -1, we're going to go to positive infinity. To the right of -1, we're going to go to negative infinity. To the left of positive 1, we're going to go to negative infinity. And to the right of 1, we're going to go to positive infinity. So again, I did the practice of checking both left and right hand side when we initially talked about vertical asymptotes. So if you need help with that, scroll back a little bit in the presentation. And there's no holes because nothing canceled out. Horizontal asymptote, all right, numerator is degree 0, denominator is degree 2, so the numerator is less than the denominator, and we have a horizontal asymptote at y equals 0. X-intercepts set the numerator equal to 0, but 6 doesn't equal 0, so we're good there. Y-intercept set x equal to 0, so 6 over 0 squared minus 1, 0 squared is 0, 0 minus 1 is -1, or -6, or 0, -6 is our y-intercept. And there we go. Okay, 1 over x minus 2 squared, domain, set the original denominator equal to 0, or not equal to 0, square root both sides, add 2 to both sides, and we get everything to the left of 2 with everything to the right of 2. All right, let's simplify. And we don't have any simplification to do here either. Vertical asymptote is going to be at x equals 2. And now, interesting quirk here. Notice that no matter what you plug into this function, so you take any number you want, you subtract 2, whatever it is, the second that you square it, it's going to be positive. So no matter what, we will always get a positive value for each of these, including both sides that the function approaches for the vertical asymptote. And again, nothing canceled out, so no holes. The degree of the numerator is 0, degree of the denominator is 2, so numerator is less than, we have a horizontal asymptote at y equals 0. X-intercepts, none, since the numerator still doesn't equal 0. I promise we'll look at least one example where this is different. And then y-intercept, set x equal to 0. 0 minus 2 is -2. -2 squared is +4. So 0, 1/4. And there we go. Okay, some more exciting stuff is going to happen in this one. All right, domain first, set the denominator equal to 0, subtract 2, divide by 2, and we get everything to the left of -1 with everything to the right of -1. Let's simplify. Well, in this case, also nothing to simplify. So we have a vertical asymptote at that x equals -1 that didn't cancel out. And here, just be very careful, right? In a lot of the other cases that we've had to deal with, when we plug in numbers to the left and to the right of the vertical asymptote, we normally only had to plug things into the denominator, but be careful because now you need to plug in that value into every x that you see, not just the denominator. So doing so, to the left of -1, you'll get positive infinity, and to the right of -1, you will get negative infinity. Still nothing canceled out, so still no holes. Okay, degree of the numerator is x to the 1, 1. Denominator is 2x to the 1. So for the first time, the degrees are equal. So there's a horizontal asymptote at y equals x over 2x. Take those leading terms and divide them. Cancel out an x, we get 1/2. So we have a horizontal asymptote at y equals 1/2. X-intercepts. X-intercepts say to set the numerator equal to 0. Oh, finally we can do that. Add 3 to both sides, and we get 3, 0. Y-intercept, set x equal to 0. So we get negative 3 at the top, 2 at the bottom. So 0, comma, negative 3 over 2. All right. And 2 more examples, and then we sunset college algebra. All right, so I give you this very beautiful looking function here. I'll just give you the factored version here. Don't worry. So step 1, find the domain, set the denominator equal to 0. So we get negative 3/4 and 5/3. So that is everything to the left of negative 3/4, everything between negative 3/4 and 5/3, and everything to the right of 5/3. Simplifying the function, well, notice 4x plus 3 goes away, 3x minus 5 goes away. So we get 4x minus 9. And this is going to be a lot easier to deal with than some of the other stuff we've had to work with. Vertical asymptote, there's none. There's no more denominator. Nice. But we do have holes at those 2 x values that we canceled out. So we got to keep going. Horizontal asymptote, the degree of the numerator is bigger than the degree of the denominator since there's no more denominator. So there's no horizontal asymptote. And we knew that this is a line, so lines don't have horizontal asymptotes. X-intercepts, set the whole thing equal to 0, add 9, divide by 4, we get 9/4 comma 0, and y-intercept, set x equal to 0, well, we just get 0 comma negative 9. So kind of an interesting looking function when we do that. Okay. One more example. Let's just flip the numerator and denominator, and then we'll call it a day. Domain, set the denominator equal to 0. Oh, well, this time we actually get 3 values that this happens. So in order, we can be everything to the left of negative 3/4, everything between negative 3/4 and 5/3, everything between 5/3 and 9/4, and everything to the right of 9/4. Now let's simplify. You'll see the same 2 factors cancel out, except now we have 4x minus 9 in the denominator. So some of the rules that we just had, or some of the things we just talked about, are going to be a little opposite. So there's a vertical asymptote at this remaining term, right? 4x minus 9 didn't cancel out. So we have a vertical asymptote at 9/4. To the left of 9/4, it's going to be negative infinity. To the right of 9/4, it's going to be positive infinity. And we have holes at those 2 values that canceled out. Well, this time, the degree of the numerator is 0. The degree of the denominator is 1. So numerator is less than again. Horizontal asymptote at y equals 0. X-intercepts, set the numerator equal to 0. That never happens. So we have y-intercept when x is equal to 0. So we get negative 1/9. Very nice. And there is our graph. And that is the end of my college algebra lectures. So that's it. I like, 3.4 and 5 being the end, but sometimes we don't always have it our way. So with that said, thank you so much for watching 3.6. And if you've watched other videos, thank you so much for watching all the lectures here in college algebra. And I hope these videos have helped. So bye.
Hi everyone, thank you so much for watching. I hope this lecture helped and that you learned something. Just wanted to give the brief disclaimer that this lecture for this section is based on and adapted from the section in College Algebra and Trigonometry, the 4th edition by J.S. Ratty, Marcus McWaters, and Leslavs Kazurpek. So just wanted to give that disclaimer. I'm not affiliated with any of the authors. I'm not affiliated with Pearson, the publisher. This is entirely a presentation and lecture I created based on the book. So thank you so much for watching, and see you in the next section.